Before we begin, consider a quiet question that hides beneath everything you have ever touched. If you drop a stone, why does it fall? The answer seems so obvious that it almost escapes attention. Yet hidden beneath that simple motion lies a riddle that has challenged every generation of science. What invisible agent curves the path of planets, pulls oceans upward into tides, and orders the slow dance of galaxies across unfathomable distances? And if gravity is truly a force, why does it behave unlike any of the others that quantum theory describes with such precision? Somewhere between falling bodies and the fabric of the universe stretches a puzzle that grows sharper the deeper we look. Could the space around you, the distance between your hand and the floor, even the passage of time itself, be less fundamental than they appear? Gravity enters a human life before language does. An infant feels its pull long before the world is divided into objects and names. The downward tug seems ordinary, but familiarity hides complexity. Each moment a person stands upright against the steady draw of the earth, they are held in place by a phenomenon that shapes planets, stars, and the great structures of the cosmos. From the gentle fall of a leaf to the sweeping arcs traced by worlds around their stars, gravity works in silence, guiding motions that appear effortless. Its presence feels so natural that it is easy to forget how strange it truly is. When a stone slips from a hand and accelerates toward the ground, the simplicity of the event masks a mystery that reaches from the earth to the edge of the observable universe. Isaac Newton was the first to reveal that the same rule governing a stone's fall also governs the movement of the moon and the paths traced by the planets. By carefully measuring the way bodies accelerate and comparing these motions across vast spaces, he recognized a pattern. Every mass pulls on every other mass, he concluded, with a strength that increases with the size of the masses and diminishes with the square of the distance between them. Written as an equation, this insight unified earthly and celestial behaviors, weaving them into one framework. Centuries of observations supported Newton's law, allowing astronomers to predict planetary locations with extraordinary accuracy and helping explorers navigate across oceans. In an age when the true scale of the universe was still unknown, Newton uncovered a rule that stretched far beyond the Earth. Yet even as Newton's law succeeded, subtle irregularities began to whisper of deeper truths. Mercury, the innermost planet, refused to follow predictions with perfect obedience. Its orbit shifted slightly, precessing around the Sun in a way that Newton's equation could not fully explain. For many years, this discrepancy remained a small puzzle, and astronomers wondered whether an unseen planet or slight measurement errors might be responsible. The answer waited for a new way of understanding gravity, one that would replace Newton's invisible pulling force with something more fundamental. That understanding arrived with Albert Einstein. Instead of treating gravity as an interaction between masses, Einstein reimagined it as a property of space itself. According to his insight, space and time form a single, flexible fabric. Matter and energy bend this fabric, and the curvature guides the motion of bodies. A planet does not orbit because it is being pulled along a path, but because it travels through curved space, following the straightest path allowed by the geometry. This idea seemed radical at first, yet it explained Mercury's stubborn orbit with elegant precision. The additional curvature near the Sun nudged Mercury's path just enough to account for the long-observed precession. Einstein's theory offered predictions that went far beyond Mercury. Light passing near the Sun should bend as it follows the curved geometry. Time should pass more slowly in stronger gravitational fields. Clocks carried to higher elevations should tick slightly faster than those kept near the surface of the Earth. Every prediction was testable, and over the years each one was confirmed. During a solar eclipse in the early 20th century, astronomers measured starlight bending around the Sun. Later experiments verified gravitational redshift and the slowing of time in stronger fields. In the 21st century, detectors like LIGO and Virgo recorded ripples in spacetime itself, created when black holes collided. These gravitational waves, moving across the universe at the speed of light, matched Einstein's equations with striking accuracy. Yet beneath these triumphs lies a quiet problem. Einstein's theory describes gravity with unmatched clarity on large scales, from planets to galaxies, to the observable universe. But it remains a classical theory. It does not include the rules that govern atoms, particles, and the strange fluctuations that fill the quantum world. Every other fundamental interaction fits comfortably inside quantum mechanics. Gravity alone stands outside. When physicists try to combine Einstein's geometry with quantum fields, contradictions appear. At extremely small scales, where quantum uncertainty dominates, the smooth fabric of spacetime predicted by general relativity begins to break down. This mismatch between the classical and the quantum is not a minor gap. It is one of the deepest unresolved issues in physics. General relativity works beautifully when dealing with stars and planets, while quantum mechanics works flawlessly for particles. But the universe does not separate these domains. In the heart of a black hole, and in the earliest moments after the beginning of cosmic expansion, gravity and quantum effects converge. Without a unified framework, the description of nature becomes incomplete exactly where the most extreme phenomena occur. This tension motivates a profound question. If gravity cannot be fully described within classical geometry, what lies beneath that geometry? Could spacetime itself, the very stage on which physics unfolds, be an emergent structure arising from something more fundamental? The idea sounds daring, yet it is grounded in established research. Black hole thermodynamics, quantum information theory, and studies of entropy suggest that spacetime may not be the basic fabric we once believed it to be. As this chapter draws to its quiet end, the path forward becomes clear. Classical gravity explains the world we see, but quantum reality challenges its foundations. The next chapters follow this tension deeper, tracing how Einstein's geometric revolution both illuminates the cosmos and reveals its own limits. The journey ahead leads toward a striking possibility, one supported by decades of theoretical work. The universe may be holographic, and gravity may be a reflection of quantum information woven into the boundaries of space. The deeper scientists looked into gravity, the more the familiar picture began to shift. The simple pull that seemed so intuitive in daily life revealed layers of structure that demanded new ways of thinking. New tools, new experiments, and new mathematical approaches forced physics to acknowledge that gravity behaved differently from every other interaction. Electric and magnetic forces could be unified and described through quantum fields, and the strong and weak nuclear forces could be captured by intricate microscopic models. But gravity held itself apart, following rules that resisted integration into a single quantum framework. Consider the structure of the Earth itself. Every rock, every ocean, every hidden chamber beneath the crust is shaped by the inward pull of gravity. That same pull drives the tides, as the moon's presence lifts and lowers the oceans in a cycle older than any civilization. When Isaac Newton studied these motions, he saw a force acting across empty space. Yet he never claimed to understand what carried that force or how it propagated. He simply wrote a rule that matched nature with astonishing precision. For centuries, this was enough. A reliable law that worked everywhere it was tested seemed complete. But eventually questions emerged that Newton's formulation could not answer. How quickly does gravity act? Does it propagate instantly, or does it travel? In Newton's time, the idea that gravity might have a finite speed seemed unimaginable. Only in the 20th century did experiments and observations show that gravitational influence moves at the speed of light. This detail matters because a force that travels at a finite speed cannot be transmitted by simple action at a distance. It requires some medium, some structure, some geometry beneath the motion. That realization pointed directly toward Einstein's insight. Under Einstein's view, the Earth does not pull on the moon. Instead, the mass of the Earth curves the geometry around it, and the moon simply follows the natural path within that curvature. The tidal bulges rise and fall because the geometry near the Earth is not uniform. Space and time are shaped by matter and energy. Events unfold according to those shapes, and gravity is nothing more than the manifestation of that geometry. This idea replaced Newton's invisible force with a physical, dynamic space-time that bends, stretches, and evolves. The accuracy of this description is not a matter of belief. It is supported by direct measurement. Time runs at different rates depending on gravitational strength. Atomic clocks lifted to mountain altitudes tick ever so slightly faster than identical clocks kept at sea level. Photons climbing upward against gravity lose energy, shifting toward the red. Precise instruments placed in orbit show that the Earth's rotation drags space-time around with it, a prediction confirmed by meticulous experiments over many years. Astronomers see distant galaxies distorted by gravitational lensing, their shapes warped as light follows the curved geometry around massive clusters. Even the faint arcs of light seen in deep sky images confirm that Einstein's understanding of gravity is real. Then came the most dramatic confirmation of all. In the early 21st century, detectors on Earth captured the trembling of space-time itself. Two distant black holes spiraled together, compressing and stretching the fabric of the universe in rhythmic waves. Those waves traveled for unimaginable distances before arriving on Earth, where sensitive instruments recorded the faintest possible vibrations. The pattern matched exactly what Einstein's equations predicted. This single event opened a new chapter in the study of gravity. It allowed scientists to observe collisions far beyond the reach of light and to test general relativity in regimes of extreme curvature. Yet, even as these discoveries affirmed Einstein's work, they sharpened the central paradox. If space-time can bend, ripple, and stretch, then it is a physical object with structure. And if it has structure, then at the smallest scales that structure should obey quantum rules. But Einstein's theory contains no hint of quantum behavior. It treats space-time as smooth, continuous, and deterministic, while the quantum world is granular, probabilistic, and filled with fluctuations. Attempts to combine these perspectives run into infinities and contradictions. At extremely high energies, such as those found near the center of a black hole, or in the first moments of cosmological expansion, the equations of general relativity break down. This breakdown is not a minor technical inconvenience. It is the sign that the theory, powerful as it is, cannot describe the deepest workings of nature. No matter how successful general relativity remains on large scales, it is incomplete. Something must underlie its geometric picture. Something must give rise to the shape of space-time and the behavior of gravity at all levels. Physicists began to suspect that what appears simple and continuous may in fact emerge from microscopic elements invisible to the classical eye. This suspicion grew stronger as quantum theory expanded. Quantum fields do not sit quietly in space. Even in their lowest energy state, they fluctuate. Particles appear and vanish. Energy flickers. These vacuum fluctuations are real and measurable. They influence atomic behavior, electromagnetic forces, and even the mass of particles. If space-time were truly a smooth classical fabric, these quantum fluctuations would tear it apart. For the two pictures to coexist, something deeper must coordinate their behavior. That realization set the stage for one of the great transitions in modern physics. By the end of the 20th century, evidence from black hole thermodynamics, quantum field calculations, and studies of entropy suggested that space-time might not be fundamental. Instead, it could be emergent, arising from quantum interactions that encode information in ways not yet fully understood. This possibility changes the question entirely. If space-time emerges from something else, then gravity itself must also emerge as a collective phenomenon, much like temperature arises from countless microscopic motions. That idea is not speculation in the loose sense. It is grounded in precise calculations and decades of peer-reviewed research. But to understand how such a profound shift became plausible, one must first return to the puzzles hidden inside black holes. They hold clues that challenge the smooth fabric of space-time and point toward a deeper, holographic layer of reality. The path from everyday gravity to the mysteries hidden in black holes may seem long, yet the two are woven together by the same underlying question. If gravity bends the light of distant galaxies and shapes the orbits of planets, what happens when its pull becomes so intense that even light cannot escape? In ordinary circumstances, gravity reveals itself through gentle motions, subtle curvatures, and the slow drift of celestial bodies. But near the surface of a black hole, the effects become extreme. There, space-time is curved so strongly that all familiar intuitions collapse. These regions test the limits of both general relativity and quantum mechanics, forcing physicists to confront the shortcomings of each theory. A black hole forms when enough mass is compressed into a small enough region. The resulting curvature grows so strong that a boundary forms around it, a surface from which nothing can return once crossed. Einstein's equations describe this boundary with remarkable precision, yet the mathematics produces a troubling implication. As one approaches the very center of the black hole, the curvature grows without bound. The equations predict a singularity, a point where density becomes infinite and space-time ceases to behave in any defined way. Such a prediction is a clear sign that general relativity is being pushed beyond its domain. No physical measurement has ever confirmed the existence of an actual infinite density. Instead, the singularity signals the need for a deeper theory, one that unites gravity with the quantum world. The quantum perspective adds another layer of complexity. According to quantum field theory, every region of space contains fields that fluctuate endlessly. Near the boundary of a black hole, known as the event horizon, these fluctuations behave differently from what happens in ordinary space. Stephen Hawking studied these effects and discovered that black holes are not perfectly dark. Instead, they emit a faint thermal glow. Particles appear just outside the horizon, carrying energy away. Over immense spans of time, this radiation causes black holes to slowly lose mass. This insight links gravity and quantum mechanics in a way that neither theory can fully explain on its own. The radiation predicted by Hawking has a temperature, and the horizon has an entropy. Entropy is a measure of information, a count of how many microscopic configurations could give rise to the same macroscopic state. For ordinary matter, entropy scales with volume. A larger region contains more room for microscopic details, but the entropy of a black hole behaves differently. It is proportional not to the volume enclosed by the event horizon, but to the surface area of that horizon. This discovery shocked physicists because it suggested that the information content of a region of space might reside not inside the volume, but on the boundary. This area scaling is not an approximation. It is a precise relationship supported by rigorous calculation. It challenges the intuitive picture of space-time as a volume filled with degrees of freedom. Instead, it hints that the number of fundamental degrees of freedom inside a region may be limited by the surface that encloses it. That idea forms the seed of a profound shift in modern physics. If information in a black hole is encoded on its boundary, perhaps space-time itself is organized in a similar way. This realization deepened the unresolved tension between quantum mechanics and general relativity. General relativity insists that information falling into a black hole disappears behind the horizon, continuing toward the singularity. Quantum mechanics insists that information cannot be destroyed. Both principles are deeply embedded in their respective theories, yet they contradict one another at the threshold of a black hole. The conflict between them is known as the black hole information paradox. It remains one of the central problems in theoretical physics, and it points toward the need for a new framework that respects both quantum rules and the geometric nature of gravity. This paradox does not arise from speculation. It arises from combining well-tested principles. General relativity accurately describes the curvature of spacetime in strong fields. Quantum mechanics accurately describes how particles and fields behave. Both have been supported by decades of experiments. Yet when applied together to black holes, they produce incompatible conclusions. For physicists, such a conflict serves as a guide. It reveals where current theories must be extended or replaced, and it suggests that gravity may not be fundamental in the way once imagined. Over time, evidence accumulated from many directions. Studies of quantum fields in curved spacetime showed that the behavior of particles depends on the observer's motion. Insights from thermodynamics revealed that horizons behave like physical surfaces with temperature and entropy. Advances in quantum information theory demonstrated that entropy, entanglement, and information storage play crucial roles in describing both quantum systems and gravitational ones. These threads began to weave together into a new picture, one in which spacetime might emerge from underlying microscopic processes that organize information in specific ways. At this point, the mystery expands beyond black holes. If the entropy of a horizon is tied to its surface area, and if the information of a region is bounded by that area, then the entire concept of volume-based degrees of freedom may need revision. Such a revision carries profound consequences. It suggests that the smooth geometry described by Einstein might arise from a deeper layer of quantum structure, one that is not spatial in the ordinary sense. Instead of treating spacetime as the foundational backdrop, physicists began to consider whether it could be the result of collective behavior, much like how a fluid arises from countless interacting molecules. This emerging idea does not undermine the success of general relativity. On the contrary, it explains why Einstein's equations work so well on large scales. If spacetime is emergent, its large-scale behavior would naturally appear smooth and classical, even if its microscopic origin is quantum and discrete. In this sense, gravity could resemble other collective phenomena. Temperature, for example, is not a property of a single particle. It emerges from many particles interacting. Pressure, similarly, arises from countless collisions within a gas. Gravity might stand in the same category, a macroscopic phenomenon that expresses the averaged behavior of quantum information. As this chapter prepares to transition into the next, the central idea becomes clear. Gravity began as the simple pull that shapes falling objects and planetary orbits. It evolved into the curvature of spacetime, confirmed by precise measurements and monumental experiments. But at its deepest level, the same force that guides apples and galaxies reveals contradictions that cannot be ignored. Black holes show that information must be accounted for. Quantum theory demands microscopic consistency. The surface area scaling of entropy hints that spacetime may carry less information than its volume suggests. All these clues point toward a striking possibility that reshapes the path ahead. The next chapter steps directly into Einstein's geometric revolution. It examines how general relativity redefined gravity, why the theory works so brilliantly, and where it inevitably reaches its limits. Those limits open the door to a profound revelation, one that leads directly toward the holographic nature of spacetime itself. The story of gravity changed forever when Albert Einstein began to question the assumptions that had guided physics for centuries. Newton's law described the force between masses with unmatched accuracy, but it offered no explanation for what carried the interaction or why it acted the way it did. Einstein approached the problem from a different angle. Instead of asking how masses pull on one another, he asked whether space and time themselves might hold the answer. That single shift in perspective transformed the understanding of gravity into something deeper, something woven into the very structure of the universe. Einstein began with a simple yet powerful observation. A person falling freely in a gravitational field feels nothing. Inside a falling elevator, a dropped object floats as if gravity had vanished. The sensation of weight disappears. This insight became known as the equivalence principle, the idea that free fall is indistinguishable from weightlessness. To Einstein, this was not a mere curiosity. It hinted at a unity between inertial motion and gravitational motion. If all objects fall in the same way regardless of their mass, then gravity might not be a force in the traditional sense. It might be a feature of the arena in which motion takes place. Guided by this idea, Einstein imagined space and time not as separate, rigid entities, but as one continuous, malleable fabric. Mass and energy, he realized, do not simply reside within this fabric. They shape it, they bend it, and once curved, the fabric guides the paths that objects follow. A rock thrown into the air, a planet orbiting a star, even light itself moves along the natural lines drawn by this curvature. These natural lines are known as geodesics, the straightest possible paths allowed by the geometry. What seems like a force pulling objects is instead the result of objects following the geometry imposed by mass and energy. This picture is more than a metaphor. It is encoded in the field equations that Einstein discovered, equations that relate the curvature of spacetime to the distribution of mass and energy within it. Although the full mathematical form is intricate, the conceptual message is simple. Geometry responds to matter, and matter responds to geometry. This mutual relationship replaces Newton's instant action at a distance with a dynamic, local interaction, where variations in spacetime propagate at the speed of light. The accuracy of Einstein's theory appeared quickly. It resolved the long-standing puzzle of Mercury's orbit by accounting for the additional curvature near the Sun. It predicted that light would bend when passing near a massive object. It foretold that time would slow down in stronger gravitational fields, and that clocks would run faster where gravity is weaker. Over the decades, these predictions were tested through eclipses, satellite clocks, and astronomical observations. Each experiment confirmed the theory with increasing precision. As technology advanced, so did the ability to probe the fabric of spacetime more directly. Observations of distant galaxies revealed dramatic arcs of distorted starlight, signatures of gravitational lensing. Measurements from orbiting gyroscopes confirmed that the Earth's rotation drags spacetime around with it. Most strikingly, the detection of gravitational waves offered direct evidence that spacetime is not merely a backdrop, but a dynamic entity capable of carrying energy across the cosmos. Colliding black holes created ripples that traveled for immense distances before reaching detectors on Earth, their patterns matching Einstein's predictions almost perfectly. Yet these extraordinary successes conceal a profound limitation. Einstein's description of spacetime is classical. It treats geometry as smooth and continuous, a surface without granularity. But quantum mechanics describes the world as fundamentally uncertain, filled with fluctuations that cannot be ignored. When physicists attempt to quantize spacetime in the same way they quantize electromagnetic or nuclear fields, the mathematics becomes unstable. Curvature grows wildly at extremely small scales, and calculations produce infinities that cannot be removed. The smooth fabric that Einstein envisioned begins to unravel when viewed at the quantum level. This conflict becomes most visible at the Planck scale, a realm far smaller than any particle that has ever been observed. At such scales, quantum uncertainty dominates. Distances lose their ordinary meaning. Energy fluctuates in violent bursts. Under these conditions, the equations of general relativity simply cannot function. They predict curvatures so extreme that spacetime tears itself apart. No physical experiment has ever reached these energies, yet the mathematics reveals that the theory cannot be complete. It fails at the very places where quantum and gravitational effects must merge. The problem grows even sharper inside black holes and in the earliest moments of cosmic expansion. Near the singularity predicted by general relativity, curvature becomes infinite, time loses meaning, and the equations offer no further guidance. These singularities are not physical objects. They are signs that the theory has reached its limit. A complete description of nature must avoid such breakdowns. It must remain meaningful even at the highest energies, where quantum fields and spacetime geometry meet in their most intense form. This need for a deeper theory is not merely philosophical. It is driven by the requirement of consistency. Quantum mechanics insists that uncertainty governs all physical systems. General relativity insists that geometry is smooth. These statements cannot both be true at all scales. The universe cannot be governed by two incompatible descriptions. Somewhere, beneath the classical geometry of Einstein and the probabilistic rules of quantum theory, there must be a single framework that includes both. Physicists began to suspect that continuous geometry may not be fundamental. Perhaps the smooth spacetime Einstein described is an emergent approximation, much like how a flowing liquid appears smooth, even though it is made of molecules. If spacetime emerges from something microscopic, then the breakdown of general relativity at extreme scales becomes natural. The theory works beautifully when the emergent structure is stable and smooth, but it fails where the underlying components dominate. The search for those components and for the principles that govern them defines the quest for quantum gravity. This search leads directly into the next chapter. To understand why space-time cannot remain classical in a quantum universe, one must examine the structure of quantum fields themselves. Their fluctuations, their entanglement, and their behavior in curved environments challenge every classical assumption. They reveal that the smooth fabric Einstein described cannot survive as a fundamental entity. Instead, it must arise from something deeper, something capable of weaving information, energy, and geometry into one coherent whole. Einstein's geometric insight transformed gravity into a manifestation of space-time itself, a view so elegant that it reshaped the scientific imagination. The idea that mass and energy bend the geometry in which all motion occurs gave the universe a new coherence. Planets follow curved paths, not because they are pulled, but because their natural trajectories lie within warped space-time. Light bends not because it feels a force, but because the geometry through which it travels is distorted. This vision carries a beauty that continues to inspire. Yet beauty does not guarantee completeness. As physicists studied the implications of this geometric picture, cracks began to appear in places where the theory encountered extremes. One of the earliest signs came from the study of gravitational collapse. When a massive star exhausts its fuel, it can no longer support itself against its own weight. The outer layers fall inward. As the collapse accelerates, the curvature grows stronger, eventually forming a boundary known as the event horizon. Beyond this boundary, nothing can escape. The geometry becomes so steep that even light is drawn inward. General relativity describes this process with great precision, predicting the shapes of horizons and the motion of matter in their vicinity. But the theory also predicts that the collapse continues indefinitely toward a point of infinite density. This singularity, where curvature becomes unbounded, signals the failure of the classical picture. No physical measurement ever indicates a true infinity. Instead, infinities reveal that the equations have reached a domain where they no longer apply. A similar breakdown appears when one traces the history of the universe backward. Observations of cosmic expansion show that galaxies are moving apart, a motion driven by the initial conditions of the cosmos. But when those equations are extrapolated to earlier and earlier times, the density and temperature rise without limit. The mathematics again produces a singularity. This singular moment cannot be the final answer. It represents a point where the theory, powerful as it is, stops describing reality. A complete theory of nature must pass smoothly through such regions, rather than collapsing into contradictions. Another challenge arises from attempts to incorporate quantum fields into curved spacetime. Quantum field theory describes particles as excitations of underlying fields that fill space. These fields fluctuate endlessly, even in their lowest energy state. Their behavior changes when the geometry changes. If space expands or curves, the quantum fields respond, and their particle content can shift. This sensitivity becomes essential when describing the early universe, where rapid expansion produced fluctuations that seeded the formation of galaxies. General relativity allows for curved backgrounds, and quantum field theory can be formulated within them, but the combination works only as a temporary truce. It cannot describe situations where quantum effects and spacetime curvature both become strong. the two frameworks were never built to coexist at a fundamental level. The limit becomes clear at the Planck scale, where distances are unimaginably small. At such scales, quantum uncertainty becomes so intense that even the concept of distance begins to blur. Energy fluctuations in tiny regions of space grow so large that they can create miniature distortions in geometry. These distortions feed back into the quantum fields, creating a storm of fluctuations that neither theory can control. General relativity predicts precise geometry, but fails when confronted with extreme quantum uncertainty. Quantum field theory relies on a fixed background spacetime, but fails when the background itself becomes unpredictable. Each framework depends on assumptions the other violates. This mutual incompatibility shows that general relativity, despite its elegance, is not the final description of gravity. Its geometric laws describe the world on large scales, but they cannot be extended indefinitely. Whenever curvature becomes too strong or distances become too small, the smooth fabric Einstein envisioned tears apart. At those moments, the theory stops being a reliable guide. A deeper framework must take its place, one that incorporates both geometry and quantum rules in a single, consistent structure. Hints of this deeper structure appear not only in singularities, but also in the behavior of horizons. The surface of a black hole is not merely a geometric boundary. It behaves like a physical system with temperature and entropy. These properties cannot be explained by classical geometry alone. They reveal that horizons contain microscopic degrees of freedom, elements that encode information in ways the classical theory does not address. The surface area law for black hole entropy shows that the amount of information is tied not to volume, but to area. This surprising relationship suggests that the true degrees of freedom of spacetime may reside not within regions, but on their boundaries. This possibility aligns with a broader trend in physics. Whenever a classical theory reveals boundaries where its predictions fail, the resolution often lies in identifying the microscopic constituents from which the classical description emerges. A fluid behaves smoothly at large scales, but at microscopic scales it is made of atoms. A magnetic field behaves continuously, but its origin lies in discrete spins. In both cases, the classical laws are successful because they describe collective behavior. They are not fundamental. If spacetime shares this pattern, then Einstein's geometric revolution may be the large-scale manifestation of deeper quantum interactions. Such a viewpoint does not diminish the power of general relativity. Instead, it explains why the theory functions so well across a vast range of scales. In regions where curvature is gentle and quantum effects are small, the emergent geometry remains smooth, and Einstein's equations hold their precise form. But where curvature grows extreme or quantum fluctuations dominate, the underlying structure takes over and the classical geometry fails. This is not a flaw. It is a clue pointing toward the next layer of understanding. Physicists around the world have spent decades searching for this next layer, exploring a variety of approaches. String theory proposes that the fundamental components are not particles, but extended structures. Loop quantum gravity suggests that spacetime itself is discrete. Other approaches seek to derive spacetime from the entanglement patterns of quantum states. While none of these attempts have yet provided a complete solution, they share a common insight. The smooth geometry of Einstein is unlikely to be fundamental. It must arise from something deeper. As these ideas gathered momentum, a new image of spacetime began to form. Instead of a continuous stage where events unfold, spacetime could be a collective phenomenon built from relationships among microscopic elements. These elements might not be spatial at all in the usual sense. They could be patterns of entanglement, networks of information, or quantum states evolving according to rules that do not rely on classical geometry. Under the right conditions, these structures could knit together into a smooth spacetime. Under extreme conditions, they would reveal their underlying form. The next part of this chapter continues this transition. To fully understand why the smooth fabric of Einstein must give way to quantum structure, one must explore the specific ways in which the classical theory breaks down. These failures are not merely mathematical curiosities. They mark the points where the universe itself demands a more complete description. And in meeting that demand, physicists take the first steps toward the holographic view of space-time. The growing realization that Einstein's geometric theory cannot stand alone marks one of the most important turning points in modern physics. The elegance of curved space-time explains so much, yet its very success draws attention to the places where it falters. These points of failure do not weaken the theory in a practical sense, for general relativity continues to describe astronomical phenomena with unmatched precision. Instead, they illuminate its boundaries. A map is most revealing not only where it is accurate, but where it ends. The universe draws those boundaries with unmistakable clarity, and each boundary points toward an underlying structure that general relativity cannot describe. One of the clearest boundaries appears in regions where curvature becomes unbounded. At the center of a black hole, or at the earliest instant of cosmic expansion, the mathematical form of spacetime warps so violently that the equations of general relativity lose meaning. The appearance of infinite density or infinite curvature is not a prediction about physical reality. It is a sign that the model itself has reached its limit. No theory that produces infinities in this way can be fundamental. Rather, it functions as an approximation that eventually gives way to something deeper. Another boundary emerges when one considers the energy carried by gravitational waves. These waves are ripples in the geometry itself. They propagate across the universe and can interact with matter. Yet when one attempts to combine these waves with quantum rules, difficulties arise. The curvature they represent cannot be quantized in the same straightforward way as electromagnetic fields. The mathematical tools that work so well in quantum field theory fail to tame the divergences that appear when space-time itself becomes a quantum object. Calculations that rely on smooth geometry run into infinite corrections. Attempts to remove these infinities do not succeed as they do in other quantum theories. The structure itself resists the conventional methods of quantization. A third boundary becomes clear when examining the behavior of quantum matter in strong gravitational fields. Quantum fields respond to curvature by shifting their patterns of fluctuation. Particles may appear where none existed. Energy may flow between fields and geometry in unexpected ways. These effects are not flaws, but features of the quantum description. Yet the classical geometry of Einstein cannot accommodate all of them. The geometry has no built-in concept of quantum uncertainty or entanglement. It cannot encode the microscopic information that quantum theory demands. Whenever these microscopic effects become important, the classical geometric picture becomes incomplete. The incompatibility deepens when one considers what happens at very small distances. In quantum mechanics, uncertainty limits the precision with which positions and energies can be known. If one tries to probe distances smaller than the Planck length by concentrating more and more energy into a small region, the energy itself distorts spacetime. The region collapses into a black hole before any information about the microscopic structure can be extracted. This behavior shows that spacetime cannot be treated as a passive container. It reacts to attempts to measure it. The very act of probing small distances changes the geometry in fundamental ways. This interplay between measurement and curvature reveals that the smooth continuum Einstein described cannot survive arbitrary magnification. Beneath it must lie some other structure, one that does not rely on continuous geometry. These boundaries point toward a single conclusion. General relativity does not contain the ingredients needed to merge with quantum theory. It is a powerful approximation, valid whenever curvature is gentle and quantum effects are weak. But it cannot describe conditions where both are strong. A deeper theory must provide a microscopic foundation for spacetime, one that explains when and how Einstein's equations emerge. Such a theory must incorporate the laws of quantum mechanics, including uncertainty, entanglement, and information flow. It must also reproduce the geometric behavior observed on large scales. The search for such a theory is one of the central goals of modern physics. Clues toward this deeper structure appear when physicists examine the thermodynamic properties of horizons. The temperature and entropy associated with black hole horizons arise directly from quantum effects in curved spacetime. These quantities are measurable in principle and calculable in practice. Their existence implies that horizons contain a large number of microscopic degrees of freedom. Yet general relativity, in its classical form, contains no such degrees of freedom. For the theory to be consistent with horizon thermodynamics, spacetime must have a microscopic structure that stores information in a way the classical equations do not reveal. The relationship between entropy and surface area strengthens this conclusion. That entropy scales with area rather than volume suggests that the underlying degrees of freedom live on lower dimensional boundaries. This is not a conjecture of convenience. It follows from precise calculations and has been confirmed through multiple independent approaches. The idea that the universe stores information on surfaces rather than within volumes challenges the intuitive picture of space as a three-dimensional container. It instead hints that the geometry we experience emerges from deeper principles in which information and quantum correlations play central roles. These insights lead naturally toward the holographic principle, the idea that a gravitational theory in a region of space can be described by a theory defined on its boundary. The principle grew from the realization that information content is limited by surface area and not by volume. While the full development of the holographic principle belongs to later chapters, its roots lie in the breakdowns and clues explored here. General relativity cannot itself be the fundamental story. The emergence of entropy, the behavior of quantum fields, and the unavoidable appearance of singularities all point toward a deeper framework. Physicists often describe the situation by saying that spacetime must be quantized, but this phrase can mislead. It suggests replacing a smooth fabric with a grid of tiny units. The deeper idea is more subtle. Spacetime may not be fundamental at all. It may be a large-scale manifestation of structures that do not resemble space or time in any classical sense. Just as temperature emerges from the collective motion of molecules, spacetime may emerge from the collective behavior of quantum information. Under normal conditions, the emergent geometry appears smooth. Under extreme conditions, the underlying structure reveals itself. These ideas set the stage for the next chapter, which explores how quantum mechanics challenges the continuity and certainty of classical geometry. The quantum world does not respect smooth surfaces or deterministic trajectories. It introduces fluctuations, entanglement, and uncertainty that reshape the understanding of what space-time can be. By examining these quantum effects, one begins to see why general relativity must give way to a deeper description and how that deeper description hints at a holographic universe. Quantum mechanics entered physics like a quiet storm. It began as a set of puzzling observations about atoms and light, small anomalies that resisted the logic of classical theories. Then it grew into a complete framework, one that described the world with new rules that seemed at first contradictory to common intuition. What began with the behavior of electrons and photons soon expanded into a universal language, a language that explained the stability of atoms, the structure of matter, and the properties of every known particle. Yet, as quantum mechanics grew in precision and scope, it began to press against the foundations of Einstein's geometry. The clash between these two pillars revealed that the smooth fabric of spacetime cannot survive untouched in a quantum universe. Quantum mechanics describes nature through probabilities, wave functions, and operators that do not always commute. It teaches that particles do not follow single definite paths. Instead, they explore every possible route between 2 points, with the final outcome determined by the interference of all those possibilities. This behavior is not merely conceptual. It governs the results of experiments with extraordinary accuracy. Interference patterns, tunneling phenomena, and discrete energy levels confirm that quantum rules are real. They apply at scales from atoms to molecules, and even to some macroscopic systems under extreme conditions. Nothing in these rules resembles the deterministic and smooth geometry that general relativity describes. Yet despite their differences, general relativity and quantum mechanics must coexist. The universe contains both atoms and curved spacetime. Quantum fields must vibrate within the geometry that Einstein described. But the moment one tries to combine these two frameworks, contradictions arise. The quantum vacuum, far from being empty, is filled with restless fluctuations. Even when no particles are present, energy flickers in and out of existence. These fluctuations can shift the motion of electrons, alter the behavior of atomic clocks, and influence the forces between particles. In a classical spacetime, these fluctuations would exert gravitational effects. They would curve spacetime in unpredictable ways. But general relativity contains no mechanism to incorporate such restless motion. It treats the vacuum as empty, a smooth stage without features. This tension becomes vivid when one examines the idea of a quantum field. A quantum field is not a thing that sits quietly in space. It is the fundamental entity from which particles emerge. Every point in space contains fields, and each field fluctuates with a minimum energy that cannot be removed. These zero-point energies should, in principle, contribute to the curvature of space-time. Yet if one adds up the expected contributions from every field at every possible energy, the predicted curvature becomes enormous, far larger than anything observed. The fact that space-time remains smooth instead of violently distorted reveals that general relativity and quantum field theory cannot be combined by simply adding their results. A deeper structure must reconcile these pieces. The incompatibility becomes sharper when one considers entanglement. When two particles become entangled, their properties link in ways that defy classical explanation. Measuring one particle instantly determines the state of the other, even across great distances. This phenomenon does not violate causality, but it challenges the classical notion that physical properties are localized. Entanglement shows that information and correlations can span space in ways not captured by classical geometry. Yet if space-time were fundamental and continuous, entanglement would have no natural place within it. The phenomenon does not fit into a picture built solely from points and distances. It belongs to a deeper layer of quantum structure. This deeper layer becomes unavoidable when examining black hole thermodynamics. The discovery that black holes radiate with a temperature and possess entropy brought quantum mechanics into direct contact with the strongest gravitational fields. Hawking showed that radiation arises from quantum fluctuations near the horizon. These fluctuations depend on the geometry, but they also modify it. The temperature of a black hole is inversely proportional to its mass. This relationship reveals that the horizon behaves like a thermodynamic object, one with internal microstates. Yet general relativity, in its classical form, contains no microstates. It treats the horizon as a smooth, featureless surface. The fact that entropy scales with horizon area rather than volume is even more revealing. It means that the information content of a region of space is proportional to its boundary, not its interior. This area law signals a profound departure from the expectations of classical geometry. In ordinary thermodynamic systems, entropy grows with volume. A larger container holds more molecules and therefore more microscopic states. But a black hole does not follow this pattern. Its entropy grows only with the area of its horizon. This behavior suggests that the true degrees of freedom associated with gravity do not reside within the volume of spacetime. Instead, they live on the boundary. Such a conclusion does not arise from speculation. It arises from precise calculations that combine quantum theory, thermodynamics, and the geometry of horizons. The area law also hints that spacetime might be encoded in ways that resemble quantum information. If the bulk of spacetime contains no more degrees of freedom than its surface area, then the smooth three-dimensional world may be a large-scale representation of a lower dimensional structure. This idea forms the first step toward the holographic principle, which states that a gravitational theory in a region can be equivalent to a theory defined on its boundary. But before the holographic principle can be introduced, one must acknowledge that quantum mechanics has already undermined the classical assumption that spacetime is continuous and fundamental. Another challenge arises from the information paradox. General relativity predicts that information falling into a black hole disappears forever behind the horizon. But quantum mechanics insists that information cannot be destroyed. The evolution of a quantum system must preserve the total information contained within it. These two views cannot be reconciled under a purely classical picture of spacetime. The paradox forces physicists to question whether the horizon is a smooth geometric surface or whether quantum structure alters it in ways that preserve information. The detailed nature of this alteration remains the subject of active research, but the paradox itself is undeniable. It reveals that classical geometry cannot fully describe what happens near horizons. The contradictions between quantum rules and classical geometry also show up in theoretical attempts to quantize gravity directly. Techniques that successfully quantize electromagnetism or nuclear forces fail when applied to spacetime curvature. The infinities that appear cannot be renormalized away. This failure suggests that geometry itself cannot be the starting point for a quantum theory. Instead, geometry might emerge from something more fundamental, something that naturally incorporates entanglement and quantum fluctuations. These themes converge toward a single lesson. The smooth fabric of spacetime that Einstein envisioned cannot be the ultimate description of reality. It is a powerful and accurate approximation at large scales, but it dissolves when confronted with the microscopic rules of the quantum domain. To move forward, physics must uncover what lies beneath the geometry. The clues point toward information, entropy, quantum correlations, and surface-based degrees of freedom. They also point toward black holes, which act as windows into the quantum structure of spacetime. As this part draws to a close, the path ahead becomes unmistakable. Quantum mechanics does not simply challenge classical geometry, it reshapes the entire framework. The next part will continue this journey by examining how these quantum tensions lead directly into the holographic principle, one of the most transformative ideas in modern theoretical physics. Quantum mechanics reveals that the world is never still. Even a vacuum, which classical physics imagined as a perfect emptiness, becomes a restless ocean of activity. Fields fluctuate endlessly, creating brief appearances of particle pairs that dissolve as quickly as they form. This ceaseless motion cannot be removed. It is built into the structure of quantum theory itself. The vacuum becomes a sea of energy, and yet this sea does not distort the universe in the catastrophic way that simple calculations might imply. This mismatch illustrates the depth of the tension between quantum theory and the smooth geometry Einstein described. The fabric of spacetime seems too calm for the restless ocean it contains. Consider how quantum fluctuations operate. Every field in the universe, whether it carries electromagnetic interactions or governs subatomic particles, possesses a lowest energy state. This state is not zero. Instead, it contains what physicists call zero-point energy. These energies, if added naively, should create a gravitational effect far stronger than anything observed. If general relativity treated these energies in the straightforward way one might expect, the entire universe would curve so intensely that it would collapse or expand uncontrollably. Yet none of this occurs. The vacuum behaves far more gently than these calculations suggest, indicating that something essential is missing from the classical picture of geometry. Another place where quantum theory undermines classical intuition lies in the behavior of particles themselves. In the classical view, a particle follows a single path through spacetime. Its motion can be traced, predicted, and described by the curvature of geometry. But quantum mechanics teaches that a particle explores all possible paths. The path we observe is the result of interference among these possibilities. This picture defies the classical idea that motion is uniquely determined by geometry. Instead, it reveals that geometry must somehow encode not only the shape of spacetime, but the full range of quantum possibilities that unfold within it. The classical concept of a definite trajectory becomes too narrow for the quantum world. Quantum mechanics also introduces the phenomenon of superposition. A particle can occupy multiple states at once. It can be in several locations, possess multiple energies, or follow different paths simultaneously until a measurement selects one outcome. This behavior is essential for the structure of atoms, molecules, and materials, yet it has no natural place in classical geometry. A point in spacetime cannot be both here and elsewhere. A classical trajectory cannot split into many possibilities. For spacetime to accommodate superposition, it must contain a deeper structure that allows reality to be described in multiple overlapping ways. This suggests that the smooth surface we call spacetime may be only one representation among many. Even more challenging is the behavior of quantum fields in curved regions of spacetime. When the geometry accelerates or bends, quantum fields respond in ways that produce particles and energy. An observer falling toward a black hole sees a vacuum, while an observer remaining stationary outside the horizon perceives a warm bath of particles. Both descriptions are correct within their respective frames, yet they contradict the classical notion that physical reality is absolute. In quantum theory, what a person observes depends on their motion through spacetime. This dependence reveals that observer-based differences are built into the foundations of quantum fields, not added later. If spacetime were truly fundamental, its geometry would be the same for every observer. The fact that quantum fields behave differently for different observers shows that classical geometry is not the whole story. The most striking example of this observer dependence is the Unruh effect. A person accelerating through empty space perceives a temperature where an inertial observer sees none. The vacuum itself appears warm. The existence of such a temperature reveals that quantum fields do not merely inhabit spacetime. They reshape its physical meaning. Temperature, energy, and particle content become sensitive to acceleration, exposing a subtle interplay between quantum theory and geometry. This interplay shows that spacetime cannot simply be a passive stage. It must emerge from a structure capable of encoding how quantum fields respond to motion and curvature. These ideas converge dramatically near black hole horizons. Hawking demonstrated that quantum fluctuations near the edge of a black hole create a stream of radiation that carries energy away. From the perspective of an observer outside the horizon, pairs of particles form near the boundary, with one falling inward and the other escaping. The escaping particle becomes part of the radiation. But the horizon does not simply emit particles. It emits them with a temperature related to the mass of the black hole. This temperature reveals that the horizon behaves like a thermodynamic surface, one with internal microscopic degrees of freedom. The entropy of a black hole strengthens this conclusion. If the horizon has a temperature, it must also have an entropy. But the entropy does not scale with the volume of the black hole. Instead, it grows with the area of the horizon. This area law defies the expectation that entropy counts internal configurations. If entropy reveals how much information is needed to describe a system, then the system's information must reside on the surface. The interior contributes none. Classical geometry offers no explanation for this strange behavior. In a classical spacetime, the interior exists. It has volume. It should contain degrees of freedom. The fact that it does not, according to quantum calculations, suggests that the classical interior is not fundamental. Something else determines the true structure of spacetime. The information paradox arises directly from these observations. If a black hole evaporates through Hawking radiation, what becomes of the information carried by the matter that fell inside? Quantum theory demands that information cannot be destroyed. The evolution of a quantum state must be reversible. But if the horizon is smooth and featureless in the classical sense, nothing could store the information that falls through. Once inside, it would be lost, contradicting quantum principles. This paradox reveals that the smooth horizon of general relativity cannot be the whole truth. Something must modify it, store information at it, or even replace it entirely with a quantum structure. In these conflicts, the message becomes unavoidable. The smooth geometry Einstein described cannot represent the deepest layer of reality. Quantum mechanics demands a microscopic foundation for spacetime, one that incorporates information, entanglement, and fluctuations. If spacetime emerges from something deeper, then the contradictions dissolve. The area law becomes natural. The information paradox becomes solvable. The behavior of quantum fields becomes consistent. But to reach this deeper foundation, one must look beyond classical geometry and into a principle that connects information with gravity in a precise and surprising way. That principle is the holographic principle, a revolutionary idea that will redefine the next chapter of this journey. It proposes that everything in a region of space can be described by information stored on its boundary. Before that idea can take shape, however, the next part of this chapter will continue exploring the key quantum clues that forced physicists to consider a holographic universe in the first place. These clues form the bridge between the quantum world and the geometric world, revealing how one might emerge from the other. The deeper physicists looked into the quantum behavior of fields and particles, the clearer it became that the classical picture of spacetime could not remain untouched. The structure revealed by quantum mechanics did not resemble a smooth geometric surface. Instead, it resembled an intricate web of correlations and information flows. These correlations existed even between regions separated by great distances, forming patterns that no classical description could capture. The more these patterns were studied, the more they pointed toward a remarkable conclusion. Spacetime might not be a fundamental arena at all. Instead, it might be the large-scale manifestation of quantum entanglement. To understand how this possibility emerged, consider entanglement itself. When two particles interact and become entangled, they form a single quantum state that cannot be separated into independent parts. This unified state contains information shared across the particles, regardless of their separation. The correlations produced by entanglement obey precise mathematical rules. These rules have been tested repeatedly, and the results always match the predictions of quantum theory. The existence of such non-local correlations implies that the universe cannot be described solely by placing objects at points in spacetime. There must be some deeper structure that determines how information links across space. These ideas gained new significance when combined with the thermodynamic properties of horizons. Hawking's calculation of radiation from black holes and the discovery that black hole entropy scales with surface area revealed that gravity carries thermodynamic features. When a black hole shrinks slightly, due to radiation, its temperature increases. This behavior mirrors the relationships seen in ordinary thermodynamic systems. Yet the microscopic picture that could explain these relationships does not appear in general relativity. The classical theory has no atoms of spacetime, no discrete bits that could combine to produce entropy or temperature. The absence of such elements forces the conclusion that spacetime must emerge from something more elemental. Jacob Bekenstein's insights strengthened this view. He recognized that there must be a maximum amount of information that can be stored within a region of space. This maximum scales with the area of the region, not its volume. The idea is known as the Bekenstein bound, and it places a strict limit on the number of degrees of freedom any physical system can contain. This limit is not arbitrary. It follows from general arguments about energy, entropy, and the laws of thermodynamics. If too much information were compressed into a region, it would collapse into a black hole. The surface area of the resulting horizon would then define the total entropy. This limit reveals something profound. The universe does not allow an arbitrary accumulation of microscopic information within a region. Instead, it restricts information to areas, not volumes. The Bekenstein-bound forced physicists to reconsider the nature of space itself. If the amount of information scales with area, then the interior of space contains no more degrees of freedom than its boundary. This conclusion cannot be explained by any classical understanding of geometry. It requires a picture in which geometry itself arises from the structure that holds this information. The traditional view of spacetime as a continuous, three-dimensional arena becomes too simple. It does not reflect the true limits imposed by quantum laws. Another key development came from studies of quantum fields near horizons. When physicists examined the entanglement between regions inside and outside a horizon, they discovered that the entanglement entropy also scales with the area of the horizon. This area scaling appears naturally in many calculations involving quantum fields. It is not an artificial imposed rule. It emerges from the mathematics itself. The area law for entanglement entropy reveals that the correlations across a boundary determine the physical behavior within a region. Once again, the bulk of space contributes nothing independent. The boundary carries the essential information. This repeated appearance of area laws became impossible to ignore. Gravity, thermodynamics, quantum fields, and entanglement all pointed toward the same conclusion. The fundamental degrees of freedom associated with a region live on its surface, not within its volume. This idea suggests that the world we experience may be similar to a hologram, where the full three-dimensional interior emerges from information encoded on a two-dimensional boundary. This comparison is not metaphorical. It arises from precise and independent lines of evidence across multiple areas of physics. The information paradox added further weight. If black holes evaporate through Hawking radiation, and if information cannot be destroyed, then the radiation must contain the information carried by the matter that fell into the black hole. But for the radiation to contain this information, the horizon itself must store and release it. This behavior contradicts the classical picture of a smooth horizon. It indicates that the horizon is not a simple geometric surface. Instead, it acts as a physical system with microscopic degrees of freedom that can encode information. The smooth horizon of general relativity must be replaced by a quantum structure that preserves information and interacts with the radiation produced near it. This conclusion is unavoidable as long as the principles of quantum mechanics remain valid. All of these clues reveal a universe where geometry is not fundamental. The smoothness of space, the continuity of time, and the familiar distances between objects may arise from an underlying quantum structure organized by entanglement. If the connections that bind quantum states determine the shape of spacetime, then gravity itself must emerge from changes in those connections. In this view, spacetime becomes a large-scale tapestry woven from entanglement, with curvature reflecting how information is distributed across the system. Such a perspective not only resolves the contradictions between quantum mechanics and classical geometry, but also provides a natural explanation for the area laws discovered in black hole thermodynamics. These developments set the stage for the next step in the journey. The pieces of evidence gathered from quantum fluctuations, black hole thermodynamics, entanglement, and information theory converge into a single insight. The universe may operate according to a holographic principle, one in which the fundamental description of a region lies on its boundary, while the interior emerges as a secondary representation. The next chapter moves directly into this idea, exploring how the behavior of black holes led physicists to propose that spacetime itself might be holographic. The holographic principle represents one of the most influential and supported advances in theoretical physics, and its origins lie in the quantum clues we have just explored. The journey toward the holographic principle begins in the most extreme environments the universe can create. Black holes, silent and invisible, press the laws of physics to their limits. They warp space-time so deeply that no signal from within their horizons can return to the outside world. They heat up through quantum effects, radiating slowly while holding secrets behind their boundaries. They store enormous amounts of entropy, despite having no internal structure in the classical sense. And above all, they reveal that the classical picture of space as a continuous three-dimensional stage, cannot be complete. The clues that point toward a holographic universe do not arise from speculation. They arise from the precise and unavoidable behavior of black holes. The earliest step toward this realization came when Jacob Bekenstein asked a deceptively simple question. If a black hole swallows matter carrying information, what becomes of that information? In ordinary thermodynamic systems, adding matter increases entropy. Entropy is a measure of the number of microscopic configurations available. But a black hole, under classical general relativity, has no microscopic structure at all. It is defined only by mass, charge, and angular momentum. If material with entropy falls into a black hole, that entropy must go somewhere. This reasoning led Bekenstein to propose that black holes themselves must have entropy. To support this idea, Bekenstein considered what would prevent a person from violating the second law of thermodynamics. According to this law, total entropy cannot decrease. But if matter carrying entropy disappeared behind a horizon that possessed no entropy of its own, the total entropy of the universe would decrease. To avoid this contradiction, the horizon must hold entropy proportional to its surface area, not its volume, but its area. This conclusion was extraordinary. It meant that the information content of a black hole was stored on its boundary. At first, this idea seemed speculative, but the situation changed dramatically when Stephen Hawking applied quantum field theory to curved spacetime near the horizon. Hawking discovered that black holes radiate. They emit thermal radiation with a temperature that depends on their mass. This radiation carries energy away, causing black holes to slowly evaporate over immense lengths of time. The temperature is small for large black holes and becomes larger for smaller ones. This behavior reveals that the horizon acts like a thermodynamic surface with well-defined physical properties. For such a surface to have a temperature, it must also have an entropy. And the entropy Hawking identified matched the relationship Bekenstein proposed. It was proportional to the area of the horizon, not the volume inside it. This revelation confirmed that the horizon contains microscopic degrees of freedom. These degrees of freedom encode information. They store the quantum details of everything that falls into the black hole. Yet the interior of the black hole plays no role in storing this information. The area law does not leave room for volume-based degrees of freedom. This structure is unlike any classical system. It implies that the true physical content of the black hole lies on its boundary. Gerard T. Hooft recognized the significance of this result. If the maximum amount of information that can be stored in a region scales with its boundary area, not its volume, then the usual view of space as filled with independent degrees of freedom cannot be correct. He proposed that all the physics inside a region might be fully described by information living on the boundary of that region. This idea became known as the holographic principle. Leonard Susskind expanded and refined it, showing that black hole thermodynamics demands such a principle. Without it, contradictions between quantum mechanics and general relativity remain unresolved. The logic behind the holographic principle is unyielding. Suppose one tries to store information within a region by placing more and more matter inside. At some point, the mass becomes so dense that the region collapses into a black hole. The maximum amount of information the region can contain is then limited by the area of the resulting horizon. No arrangement of matter can exceed this bound without collapsing. This reasoning applies to all regions of spacetime, not just to black holes. It implies that the total number of degrees of freedom available to describe a region of space is finite and proportional to its surface area. This conclusion reshapes the understanding of what spacetime is. If the interior does not contain independent degrees of freedom beyond those encoded on the boundary, then spacetime cannot be fundamental. It must arise from the structure of these boundary degrees of freedom. The three-dimensional world becomes a large-scale projection of a more fundamental two-dimensional description. The comparison to a hologram arises naturally from this relationship. A hologram stores a full three-dimensional image on a two-dimensional surface. Similarly, the physics of a region may be encoded on its boundary. This perspective resolves the information paradox in a natural way. If information is stored on the horizon, then it is not lost when matter falls into a black hole. As the black hole emits radiation, the horizon changes. The radiation must carry information away in a manner consistent with quantum mechanics. The horizon becomes a dynamic system that tracks the information content. The classical picture of a featureless membrane is replaced by a quantum structure capable of storing and releasing information. These insights were not speculative leaps. They were grounded in precise calculations and logical necessity. They emerged from thermodynamics, quantum field theory, and the geometry of horizons. But the holographic principle remained a guiding idea until Juan Maldacena provided a concrete realization of it. His work, which connects gravity in a higher dimensional space with a quantum field theory on its boundary, offered the first exact example of a holographic duality. Before exploring that duality in the next chapter, this part has laid the foundation. Black holes are not merely exotic objects. They are windows into the structure of reality. They reveal that entropy and information obey area laws. They show that horizons contain microscopic degrees of freedom. They force the recognition that space-time cannot be filled with arbitrary amounts of information. And they point toward a universe where the fundamental description of a region lies on its boundary, not in its volume. The next part will continue with the development of the holographic principle itself, tracing how this boundary-based description became one of the most influential concepts in modern theoretical physics. The idea that black holes store information on their horizons, not in their interiors, marks a turning point in the understanding of space-time. Once this idea took root, physicists began to see its implications everywhere. The horizon, a surface that once appeared passive and smooth in classical geometry, became a physical object with temperature, entropy, and microscopic degrees of freedom. These features could not be explained by general relativity alone. They signaled the presence of a deeper framework. As researchers followed this thread, they uncovered patterns that pointed toward an unexpected conclusion. The universe itself may follow rules similar to those first revealed in black holes. Gerard T. Hooft was among the first to recognize the full power of the black hole area law. He asked what would happen if a person attempted to place an enormous amount of information in a finite region of space. As more matter is added, the energy density increases. At a certain point, the accumulation becomes great enough to form a black hole. The horizon that forms has a surface area that sets the maximum possible entropy of the region. Any additional information would collapse into the black hole and increase the area of the horizon. This reasoning implies that the ultimate limit on information within any region of space is determined not by the volume, but by the surface area of its boundary. This limit is universal. It is not specific to black holes. It applies everywhere in the universe. Leonard Susskind expanded this argument and showed that it had profound consequences for the nature of physical laws. If the number of degrees of freedom in a region is constrained by the area of its boundary, then any theory that treats the interior as containing independent degrees of freedom will eventually fail. Classical field theories and quantum field theories both allow infinite degrees of freedom in any finite volume. They assume that fields can vary independently at every point in space. But the holographic limit reveals that such independence cannot be real. The number of degrees of freedom is far smaller. This realization challenges the idea that space-time points are fundamental. Instead, it suggests that the structure of space-time emerges from something else. The holographic principle was born from this understanding. It states that all the information contained in a region of space can be encoded on its boundary. This principle does not diminish the reality of three-dimensional experience. Instead, it explains why the interior behaves as it does. The interior emerges from the information stored on the boundary. Just as a hologram contains a full three-dimensional image encoded on a two-dimensional surface, the universe may contain its full physical content encoded on lower dimensional boundaries. This principle gains further support from studying the behavior of quantum fields near horizons. The entanglement between modes inside and outside a horizon naturally produces entropy that scales with the area. This entanglement entropy arises because the fields across the boundary share correlations. When an observer outside the horizon does not have access to the interior, they must describe the system using a reduced state. This reduced state contains entropy proportional to the boundary area. The appearance of area scaling in entanglement entropy provides a direct quantum origin for the thermodynamic properties of horizons. It shows that the area law is not a special feature of black holes, but a general property of quantum fields in the presence of boundaries. Other lines of evidence emerged as physicists explored the behavior of highly energetic processes. When particles collide at extremely high energy, the gravitational effects become strong enough to influence the process. If the energy is high enough, the collision can form a micro black hole. The resulting horizon once again sets a limit on the information produced. These processes reinforce the idea that information cannot be stored within a region beyond its holographic bound. Gravity enforces this limit by forming horizons whenever the bound is approached. As these ideas matured, attention turned to the structure of spacetime itself. If the true degrees of freedom live on boundaries, then the interior must arise from an encoded description. But what encodes it? How does geometry emerge from information? These questions led to a deeper exploration of the relationship between quantum mechanics and gravity. One clue came from the realization that black hole entropy is enormous. A black hole with the mass of the Sun has an entropy far greater than that of all normal matter that could be compressed into the same region. This enormous entropy suggests a rich microscopic structure behind the horizon, but this structure must reside on the surface. The classical interior plays no role in storing entropy. This boundary-based perspective resolves several long-standing puzzles. It explains why adding matter to a black hole increases its area. It explains why horizons behave like thermodynamic systems. It explains why the information paradox arises in the first place, and it suggests a natural mechanism for avoiding information loss. If the true degrees of freedom live on the boundary, then the radiation emitted from the black hole can carry information encoded in the microscopic structure of the horizon. The horizon becomes a microscopic information processor, capable of preserving and releasing information through quantum processes. Yet a principle, no matter how compelling, needs a concrete realization. The holographic principle originated as a conceptual framework. It emerged from entropy laws, information bounds, and the behavior of horizons. But concepts alone cannot replace a fundamental theory. Physicists needed an exact example, a scenario in which the full dynamics of a gravitational system could be shown to match those of a non-gravitational system defined on a boundary. Such an example would transform the holographic principle from a guiding idea into a precise duality. This exact realization arrived when Juan Maldacena discovered a correspondence between a gravitational theory in a higher dimensional space and a quantum field theory defined on its boundary. The discovery provided the first clear demonstration of the holographic principle in action. It showed that a universe with gravity could be fully equivalent to a universe without gravity, as long as the second universe lived on the boundary of the first. This startling connection revealed that space-time and gravity could emerge from the dynamics of a lower dimensional quantum theory. The next part of this chapter will continue tracing this development, linking the area law and the information bound to the concrete mathematical form of the holographic principle. That form sets the stage for the dualities that reshaped modern physics and led to the most successful example of holography known today. The holographic principle grew stronger as physicists examined more situations where gravity, quantum mechanics, and information collided. Patterns that once seemed isolated began to align. Area laws appeared not only in black hole thermodynamics, but also in the entanglement entropy of quantum fields. Information limits emerge both from thermodynamic reasoning and from gravitational collapse. Even the stability of quantum theory itself seemed to require that the number of physical degrees of freedom remain finite within any finite region. These clues formed a web of evidence pointing to a single insight. The world we experience may be a large-scale projection arising from a more fundamental layer of information stored on boundaries. One of the most compelling arguments came from examining the behavior of quantum fields in the presence of a horizon. When an observer is restricted to one side of a boundary, they cannot access the full quantum state. Instead, they must describe their accessible region using a reduced state that contains entropy. The entropy arises because information about the correlations with the inaccessible region is missing. When these calculations are performed for fields near a black hole horizon, the resulting entropy scales with the area of the horizon. This relationship mirrors the entropy formula discovered by Bekenstein and Hawking. The consistency of these results across different contexts suggests that the area law arises from the same underlying principle. The surface, not the interior, holds the essential information. This perspective reshapes the understanding of field theories themselves. Traditional quantum field theory treats spacetime as a continuous stage with infinitely many degrees of freedom assigned to each point. But if only the area of a region sets the true number of degrees of freedom, then the field theory must be an approximation. The apparent infinity of degrees of freedom becomes a convenient idealization, one that works well at low energies but must break down at high energies or strong gravitational fields. This breakdown signals that a more fundamental description must replace the field theory when approaching the limits imposed by the holographic bound. As physicists explored these ideas, they asked a natural question. If a region of spacetime truly contains no more information than its boundary, then what does the boundary theory look like? How does it encode the physics of the interior? How does geometry arise from information stored on a surface? These questions demanded a framework where the holographic principle could be demonstrated explicitly. Without such an example, the principle remained a powerful but abstract idea. The search for a concrete model intensified. Physicists wanted to see holography written into the mathematics, not just suggested by entropy bounds. Hints that such a correspondence might exist came from string theory, a framework that replaces point particles with extended objects known as strings. String theory naturally incorporates gravity and includes a rich structure of extra dimensions. While string theory remained mathematically complex, it offered tools to study quantum gravity in controlled settings. In certain cases, string theory revealed that strongly curved gravitational environments could behave as if they were governed by lower dimensional field theories. These hints remained scattered until Juan Maldacena discovered a profound and precise correspondence that unified them. Before that breakthrough, physicists explored another implication of the holographic principle. If the horizon of a black hole contains the microscopic degrees of freedom, then the classical description of the interior must be emergent. The geometry inside the horizon would not be fundamental. Instead, it would be a large-scale manifestation of the boundary theory. This insight explained why classical singularities appear. A singularity is a point where the classical description fails, not because spacetime truly ends, but because the emergent geometry no longer applies. The underlying degrees of freedom remain well defined, even if the classical picture breaks down. This understanding helps clarify why gravity behaves differently from other forces. Gravity is not a force transmitted through spacetime. It is the response of the emergent geometry to changes in the underlying information. When matter falls toward a black hole, the horizon changes. Its surface area increases in a way that reflects the additional entropy. When two black holes collide, the merging horizon grows to reflect the combined information content. This behavior mirrors the second law of thermodynamics, which ensures that entropy cannot decrease. The alignment between gravitational dynamics and thermodynamic principles is too precise to be accidental. It reveals that the laws governing horizons arise from deeper statistical rules. These insights encouraged researchers to ask how far the holographic principle extends. Does it apply only to black holes, or does it govern all of spacetime? Many lines of evidence suggest the latter. The fact that quantum fields naturally produce area scaling for entanglement. Entropy indicates that boundaries play a special role even in ordinary regions of space. The behavior of gravitational collapse shows that the interior of a region cannot support more information than its surface allows. Even cosmological horizons, which form due to the expansion of the universe, possess entropy that scales with area. The same principle appears everywhere gravity interacts with quantum mechanics. Despite this growing confidence, the holographic principle required a demonstration far more rigorous than thermodynamic arguments. Physicists needed to see the principle at work in a complete theory of quantum gravity. They needed a precise mathematical equivalence between a gravitational system in a higher dimensional space and a non-gravitational system on its boundary. Without such an example, holography remained a compelling but unproven idea. The search for this example became one of the most important efforts in theoretical physics. It was in this context that Maldacena discovered his correspondence. The correspondence showed that a gravitational theory in a space with negative curvature could be exactly equivalent to a quantum field theory defined on its boundary. This equivalence provided the first concrete realization of the holographic principle. It demonstrated that gravity and geometry could emerge from a theory without gravity. It showed that the degrees of freedom on the boundary could encode everything that happened in the interior. The interior spacetime, with all its curvature and dynamics, arose naturally from the structure of the boundary. This discovery transformed the holographic principle from a bold idea into a framework supported by precise mathematical duality. It offered a model where information, entropy, quantum fields, and geometry were united in a single picture. It showed that the surface area laws revealed by black hole thermodynamics were not isolated curiosities, but fundamental features of a deeper gravitational theory. As this chapter concludes, the next steps become clear. The holographic principle has taken shape through thermodynamics, information bounds, and the behavior of horizons. Now, it must be explored in its most successful and complete form. The next chapter will trace the development of Maldacena's correspondence, the example that revealed a holographic universe in exact detail and reshaped modern theoretical physics. The holographic principle stood for years as a powerful but abstract insight. It told physicists that the true number of degrees of freedom inside a region of space was limited by the area of its boundary. It showed that black holes store information on their horizons rather than within their interiors. It suggested that spacetime itself might not be fundamental, but instead a large-scale projection arising from microscopic rules that live on surfaces. These ideas were compelling, and they offered a unifying explanation for puzzles that classical and quantum theories alone could not resolve. Yet for all its promise, the principle remained incomplete. It needed a precise example, a case where the mathematics of a gravitational theory could be shown to match exactly the mathematics of a boundary theory with no gravity at all. That example arrived in the late 1990s, when Juan Maldacena proposed a correspondence between two seemingly unrelated theories. On one side was a theory of gravity in a spacetime with negative curvature, known as anti-de Sitter space. On the other side was a conformal field theory, a type of quantum field theory with special symmetries defined on the boundary of that space. Maldacena argued that these two descriptions were not merely similar. They were identical. Every physical quantity in one theory matched a corresponding quantity in the other. The gravitational theory and the boundary theory were two ways of describing the same underlying physics. This correspondence became known as ADS-CFT. The insight was revolutionary. It provided the first concrete demonstration of the holographic principle. It showed that a universe with gravity could emerge from a universe without gravity, and it revealed that geometry itself could arise from the structure of quantum fields living on a lower dimensional boundary. This idea reshaped modern theoretical physics, offering a new way to study quantum gravity, black holes, strongly coupled fields, and even aspects of condensed matter systems. To appreciate the depth of Moldacina's insight, one must understand the basic structure of anti-de Sitter space. Unlike the spacetime of our universe, which contains a small positive cosmological constant, anti-de Sitter space contains a negative one. This negative curvature causes the geometry to act like a gravitational well, pulling everything inward. Light and matter that move outward eventually turn back toward the center. The boundary of anti-de Sitter space lies at a finite distance, even though the interior extends infinitely. This boundary plays a crucial role. It becomes the stage on which the dual field theory lives. A conformal field theory is a quantum field theory with symmetries that relate physical quantities across different scales. It contains no intrinsic length scale. Instead, it behaves the same whether one examines it at small distances or large ones. These symmetries make conformal field theories powerful, mathematical objects. They allow precise calculations and constraints that ordinary field theories do not possess. In Moldacina's correspondence, the conformal field theory lives on the boundary of the anti-de Sitter space. The fields and operators of this boundary theory encode the full dynamics of the gravitational theory inside. This relationship is far more than a symbolic analogy. It is a mathematically exact duality. Every observable in the gravitational theory corresponds to an observable in the boundary theory. A particle moving through the bulk of the anti-de Sitter space corresponds to an operator acting in the conformal field theory. A black hole in the bulk corresponds to a thermal state in the boundary theory. Even the shape of the geometry itself corresponds to patterns of entanglement in the boundary fields. These connections are precise enough that calculations performed in one theory can be translated directly into results for the other. One of the most striking aspects of ADS-CFT is the way it handles strongly interacting systems. In many quantum field theories, strong interactions make calculations nearly impossible. But in the correspondence, a strongly interacting boundary theory often corresponds to a weakly curved classical gravitational theory in the bulk. This means that difficult problems in quantum field theory can be translated into simpler geometric problems in anti-de Sitter space. The duality provides new tools for studying systems that resist traditional methods. Black hole physics gains new clarity through this correspondence. The entropy of a black hole in the bulk matches the entropy of the corresponding thermal state in the boundary theory. This agreement confirms that the area law discovered by Bekenstein and Hawking arises naturally within the duality. The information paradox also takes on a new form. If the bulk gravitational theory is fully equivalent to a quantum field theory on the boundary, then information cannot be lost. The boundary theory obeys the rules of quantum mechanics, including unitarity. Therefore, the evaporation of black holes must also preserve information when understood from the perspective of the duality. This resolution does not rely on speculation. It follows from the exact equivalence between the two theories. ADS-CFT also reveals that spacetime geometry is deeply linked to entanglement in the boundary theory. When regions of the boundary field theory are highly entangled, the corresponding region of the bulk spacetime is smooth and connected. When entanglement decreases, the bulk geometry can become fragmented or disconnected. This connection was made precise through the Ryu-Takayanagi formula, which states that the entanglement entropy of a region in the boundary theory is proportional to the area of a minimal surface in the bulk that extends into the anti-de Sitter space. This formula provides a bridge between quantum information and geometry, demonstrating that space-time curvature emerges from entanglement patterns. These insights moved the holographic principle from a conceptual idea into a concrete scientific framework. They showed that gravity could emerge from quantum information. They revealed that geometry could be built from entanglement, and they provided a powerful tool for studying quantum gravity in a mathematically rigorous way. The implications of ADS-CFT extend far beyond anti-de Sitter space. They influence the understanding of black hole evaporation, quantum chaos, entropy bounds, and even the search for holographic descriptions of cosmology. As this part draws to its quiet close, the stage is set for the next. ADS-CFT is more than a model. It is the most successful and deeply studied example of the holographic principle. The next part of the chapter will continue exploring how this duality works in detail, why it is so compelling, and how it connects the structure of spacetime to the dynamics of quantum fields on a boundary. The discovery of ADS-CFT reshaped the landscape of theoretical physics. It offered something that had never existed before, a complete, mathematically exact example of holography. This duality did not merely echo the hints provided by black hole thermodynamics or entropy bounds. It demonstrated, with full precision, that a gravitational universe could arise from a lower dimensional quantum theory living on its boundary. What was once a conceptual possibility became a working model of quantum gravity, one capable of unifying ideas that had remained separate for decades. To understand why ADS-CFT became such a powerful tool, it is essential to appreciate how deeply the two sides of the duality align. Anti-de Sitter space, with its negative curvature, forms a natural environment for gravity. It possesses a boundary at infinity, where fields behave in well-defined ways. The conformal field theory living on this boundary lacks gravity entirely. It describes particles and fields interacting through quantum rules, with no notion of curved geometry. Yet every event in the bulk has an exact counterpart in the boundary theory. The two descriptions are different perspectives on the same underlying physics. One can imagine a particle falling toward the center of the anti-de Sitter space. From the viewpoint of the bulk, the particle moves along a trajectory determined by the geometry. But from the viewpoint of the boundary theory, the same process appears as the action of an operator spreading through the quantum field theory. The motion of the particle, the curvature of the space, and even the formation of a black hole correspond to changes in the structure of the boundary theory. Thermal states in the boundary theory correspond to black holes in the bulk. Correlation functions in the boundary theory determine the propagation of fields in the interior. In this way, geometry emerges not from classical assumptions, but from quantum behavior. One of the most remarkable aspects of the correspondence is the way it handles strong and weak interactions. Quantum field theories often contain regimes where interactions grow so strong that perturbative methods fail. Calculations become nearly impossible. Yet in the dual gravitational description, those same strong interactions correspond to weak curvature. The geometry becomes smooth and classical. This reversal transforms difficult quantum problems into tractable geometric ones. It allows physicists to compute quantities that would otherwise be inaccessible. The ability to translate strong coupling into weak curvature is one of the great strengths of ADS-CFT. Another profound insight emerges from the study of black hole entropy within the duality. Bekenstein and Hawking showed that a black hole possesses entropy proportional to its horizon area. This raised the question of what microscopic degrees of freedom produce this entropy. In ADS-CFT, the answer becomes clear. The entropy of a black hole corresponds to the entropy of a thermal state in the boundary conformal field theory. The horizon's area measures the number of boundary microstates that correspond to the same bulk geometry. This agreement confirms that the black hole entropy formula arises from the underlying quantum theory on the boundary. It is not a mysterious additional rule, but a natural feature of the duality. The information paradox also finds resolution through this framework. If the gravitational bulk description is fully equivalent to a quantum field theory on the boundary, then the evolution of the boundary theory must preserve information. Therefore, the the bulk theory cannot allow information loss, even though the classical description of black holes suggests otherwise. The apparent conflict arises because the classical geometry hides the microscopic details that the boundary theory retains. When quantum effects and entanglement are included through the duality, the evaporation of black holes becomes consistent with unitary evolution. The paradox dissolves not through speculation, but through the precise equivalence of the two theories. This equivalence offers more than solutions to old puzzles. It provides a new way to think about spacetime itself. In ADS-CFT, spacetime geometry emerges from entanglement in the boundary theory. When a region of the boundary becomes highly entangled with its surroundings, the corresponding region of the bulk becomes smooth and connected. When entanglement decreases sharply, the bulk geometry can pinch or fragment. The Ryu-Takayanagi formula makes this connection precise. It states that the entanglement entropy of a region in the boundary field theory equals the area of a minimal surface extending into the bulk. This simple yet profound statement links geometry and information in a direct and measurable way. From this perspective, geometry is not fundamental. It is a reflection of quantum entanglement. The smoothness of space-time, the curvature around masses, and even the existence of wormholes correspond to patterns of entanglement in the boundary theory. This idea reshapes the understanding of gravitational phenomena. A wormhole in the bulk corresponds to a special pattern of entanglement between two regions of the boundary. A black hole corresponds to a thermal state with large entanglement entropy. The changing shape of the bulk reflects the changing structure of quantum information. ADS-CFT also provides a laboratory for studying quantum chaos and thermalization. The behavior of black holes in the bulk mirrors the behavior of chaotic systems in the boundary theory. This connection allows physicists to use tools from statistical mechanics and quantum information to study gravity. It reveals that black holes are among the fastest scramblers of information in the universe, a property reflected in the rapid growth of certain correlation functions in the boundary theory. These insights deepen the connection between gravitational dynamics and quantum information. The influence of ADS-CFT extends beyond quantum gravity. It provides tools for studying strongly coupled systems in condensed matter physics, such as superconductors, quantum Hall states, and strange metals. These systems often resist traditional analysis, but through the duality, geometric methods in anti-de Sitter space can produce insights into their behavior. Although these applications do not describe real condensed matter systems exactly, they reveal universal patterns and offer guidance for understanding complex materials. All of these developments reinforce the central message of ADS-CFT. Gravity and geometry can emerge from quantum fields living on a boundary. The correspondence is not an approximation, but an exact duality. It provides a window into quantum gravity, a tool for studying strong coupling, and a bridge between geometry and information. It takes the holographic principle, once a bold proposal inspired by black hole thermodynamics, and turns it into a precise and calculable framework. As this part reaches its close, the path forward becomes clear. To fully appreciate the power of ADS-CFT, one must examine how geometry emerges from entanglement in more detail. The next part of the chapter will continue this exploration, describing how the duality reveals the deep structure of spacetime and why it has become one of the most trusted tools in the search for a complete theory of quantum gravity. The emergence of ADS-CFT transformed the holographic principle from an inspired idea into a robust, mathematically precise framework. Yet the true power of the correspondence lies not only in its ability to match gravitational physics with quantum field theory, but in its revelation of how spacetime itself arises from deeper structures. The duality showed that geometry is not merely compatible with quantum mechanics, it is built from it. Entanglement, correlations, and quantum information create the fabric of the higher dimensional world. This insight reshaped the pursuit of quantum gravity and illuminated the role of information in the structure of the universe. To understand this emergence, imagine the boundary theory as a vast network of quantum degrees of freedom. These degrees of freedom interact, entangle, and reconfigure themselves according to the rules of the conformal field theory. In the classical bulk description, these interactions manifest as curved geometry. When regions of the boundary become strongly entangled, the corresponding regions of the bulk connect smoothly. When entanglement decreases or breaks, the bulk geometry reflects that change, sometimes fragmenting or forming new structures. The shape of spacetime becomes a map of entanglement. The Ryu-Takayanagi formula provides the clearest link between these two pictures. It states that the entanglement entropy of a region in the boundary theory equals the area of a minimal surface in the bulk that spans the region's boundary. This formula is strikingly simple, yet its implications are profound. It means that the geometry of the bulk is determined by the entanglement pattern on the boundary. The more entanglement a region has, the larger the minimal surface becomes, and the more curved the bulk geometry appears. This relationship reveals that the curvature of spacetime emerges from the statistical properties of quantum states. Further work extended this idea. The generalization of the Ryu-Takayanagi formula to time-dependent settings showed that even the evolution of spacetime can be traced back to changes in entanglement patterns. As quantum information flows and redistributes across the boundary theory, the bulk geometry shifts in response. This dynamic view of geometry demonstrates that spacetime is not static, but continually shaped by quantum interactions. The geometry is an emergent phenomenon, one that reflects the entanglement structure of the boundary theory at each moment. This perspective provides insight into the behavior of black holes within ADS-CFT. A black hole in the bulk corresponds to a thermal state in the boundary theory. The entropy of the black hole, represented by the area of its horizon, matches the entropy of the boundary state. The growth of the horizon during black hole mergers corresponds to the increase in entanglement entropy on the boundary. The interior of the black hole, which appears mysterious in the classical theory, emerges naturally from specific patterns of entanglement. Even the potential existence of wormholes in the bulk has a boundary explanation. Wormholes correspond to entangled states, linking different regions of the boundary theory. The duality also provides a framework for understanding quantum scrambling. Black holes are among the fastest scramblers of information in the universe. The boundary theory reflects this scrambling through the rapid spread of operator growth and the mixing of quantum information. The correspondence between black hole dynamics and quantum chaos in the boundary theory offers a unified view of information spreading. It reveals that the geometric instability of black holes mirrors the sensitivity of quantum systems to small perturbations. These insights extend to the study of time itself. In ADS-CFT, the passage of time in the bulk corresponds to the evolution of states in the boundary theory. The geometry changes as the boundary states evolve. This correspondence ensures that the laws of physics remain consistent across both descriptions. It shows that bulk time is not fundamental, but emergent. It is woven from the rhythm of quantum interactions in the boundary theory. This idea reshapes the understanding of temporal evolution, suggesting that the flow of time may arise from deeper informational processes. One of the most surprising developments in the study of ADS-CFT is its connection to quantum error correction. Researchers discovered that the way bulk information is encoded in the boundary theory resembles the structure of quantum error correcting codes. These codes protect quantum information from loss or corruption by distributing it across many degrees of freedom. Similarly, the bulk geometry is protected by the entanglement structure of the boundary theory. A region of the bulk can be reconstructed from multiple different boundary regions. This redundancy mirrors the structure of quantum error correcting codes and provides an explanation for the robustness of spacetime. Even if some degrees of freedom on the boundary are altered or removed, the bulk description remains intact. These connections suggest that spacetime may be a naturally occurring quantum code. The stability of geometric structures, the resilience of horizons, and the ability to recover bulk information from partial boundary data all reflect the principles of quantum error correction. This insight offers a new perspective on the emergence of locality and causality. The bulk geometry appears local because the entanglement structure supports consistent reconstructions of bulk observables. Locality is not fundamental. It is a property encoded by the boundary theory. Through ADS-CFT, physicists gained a model where gravity, geometry, quantum mechanics, and information theory all converge. It provided a platform for exploring the microscopic origin of spacetime and the emergence of gravity from entanglement. It demonstrated that classical geometry is a macroscopic manifestation of quantum correlations, and it offered a precise mathematical structure where these ideas could be tested. As this chapter concludes, the journey turns toward the next layer of the holographic story. ADS-CFT, although powerful and precise, describes a universe with negative curvature. Our universe does not possess such curvature. It expands and contains a positive cosmological constant. The next chapter will explore the ongoing efforts to extend holography beyond anti-de Sitter space into settings that resemble our own cosmos more closely. It will examine both the challenges and the promising hints that suggest holography may reach far beyond its original domain. The holographic principle revealed that the information content of a region resides not in its volume, but on its boundary. ADS-CFT showed that a gravitational universe can emerge from a lower dimensional quantum field theory with no gravity at all. Together, these insights reshape the understanding of what spacetime is. Yet another idea took shape in the wake of these discoveries, one that revealed the true engine behind the emergence of geometry. That engine is entanglement. The quiet, invisible links that join quantum states across distance become the threads from which the fabric of spacetime is woven. Entanglement was once viewed as a peculiar feature of quantum mechanics, a strange, non-local connection between particles that defied classical intuition. Two particles could be placed far apart, yet a measurement on one would instantly shape the state of the other. These correlations could not be explained by hidden classical variables. They were purely quantum. For decades, entanglement seemed like a curiosity of microscopic systems. But as physicists explored holography, they discovered that entanglement plays a far deeper role. It determines the structure of space itself. The first hint came from asking how geometry could emerge from a lower dimensional theory. In ADS-CFT, the shape of the bulk spacetime corresponds to the pattern of entanglement across the boundary field theory. If two boundary regions share a large amount of entanglement, the bulk region between them becomes smooth and connected. If entanglement decreases, the bulk geometry stretches or even tears. This relationship suggests that spatial connectivity is not a fundamental feature, but an emergent one, built from correlations among quantum degrees of freedom. Mark van Ramsdonk made this connection vivid through a thought experiment. Imagine dividing a boundary quantum state into two halves that are initially entangled. The corresponding bulk geometry forms a connected space. Now imagine slowly reducing the entanglement between these halves. As the entanglement weakens, the bulk geometry begins to stretch. Eventually, when the entanglement vanishes, the bulk geometry splits into two disconnected pieces. Entanglement becomes the glue that binds spacetime together. Without it, there is no geometry connecting one region to another. This idea does not rely on metaphor. It reflects precise relationships within ADS-CFT. The Ryu-Takayanagi formula provides the mathematical bridge. According to the formula, the entanglement entropy of a region in the boundary theory equals the area of a minimal surface in the bulk that extends into the anti-de Sitter space. This relationship means that every entanglement pattern on the boundary has a geometric counterpart in the bulk. The more entangled two regions are, the smaller the corresponding minimal surface. The less entangled they are, the larger the surface becomes. Space-time curvature, connectivity, and even the existence of wormholes arise from these entanglement patterns. The formula was later extended to time-dependent settings, showing that bulk spacetime is not static, but evolves according to changes in entanglement. When entanglement spreads across the boundary due to interactions, the bulk geometry shifts. Surfaces expand or contract, horizons grow, throats of wormholes widen or narrow. The dynamics of spacetime become a reflection of the flow of quantum information across the boundary theory. This insight offers a new way to view gravitational evolution. Instead of arising from a fundamental geometric law, evolution arises from the rearrangement of entanglement. Another step in understanding this emergence came from examining tensor network models known as MIRA, short for Multiscale Entanglement Renormalization ansatz. These networks represent quantum states using layers of entanglement arranged at different length scales. When researchers studied the structure of MIRA networks, they noticed that the geometry formed by the entanglement links resembled a discretized anti-de Sitter space. The connections between layers of the network created an emergent geometry with properties similar to the continuous geometry of ADS. This resemblance suggested that spacetime could arise from the organization of entanglement across different scales. MIRA networks were not literal models of nature, but they revealed how natural it is for geometry to emerge from entanglement. The relationship between entanglement and geometry gained further depth through the work of Ted Jacobson. He showed that Einstein's equations, which describe how matter curves spacetime, could be derived from thermodynamic principles. If one assumes that entanglement entropy is proportional to the area of small regions, and that the flow of energy across a surface produces changes in entropy, then the familiar equations of general relativity follow naturally. This result suggests that gravity is not a fundamental force, but an emergent response of spacetime to the distribution of entanglement. Geometry behaves like a thermodynamic fluid, responding elastically to changes in information. Further developments extended this idea. Faulkner, Lukowicz, and Maldacena showed that corrections to the Ryu-Takayanagi formula produce the semi-classical Einstein equations. This result strengthened the view that gravity arises from entanglement dynamics. If entanglement changes, geometry must change. If entanglement remains uniform, geometry remains stable. The delicate balance of information and energy across a system shapes the curvature of the bulk. Einstein's equations become the large-scale thermodynamic manifestation of microscopic quantum information laws. Perhaps the most intriguing idea connecting entanglement to geometry is known as ER equals EPR. This proposal suggests that entanglement between two systems corresponds to a geometric bridge between them. In the classical picture, such a bridge resembles a wormhole. In the quantum picture, it represents entanglement. ER refers to Einstein-Rosen wormholes. EPR refers to Einstein-Podolsky-Rosen entanglement. The proposal does not claim that entangled particles contain literal wormholes. Instead, it suggests that entanglement and connectivity are two aspects of the same underlying structure. The geometry of spacetime, including wormhole-like connections, arises from entanglement patterns. As entanglement becomes stronger, the geometric connection becomes deeper. As entanglement weakens, the connection thins. When entanglement disappears, the connection breaks entirely. This perspective reveals that spacetime is a dynamic construct. It forms and dissolves according to the arrangement of quantum information. Nothing in this picture relies on speculative physics. It arises from detailed studies of holography, entropy, and gravitational thermodynamics. These insights carry a profound implication. If entanglement creates geometry, then gravity is not a fundamental interaction. It is the emergent elasticity of spacetime responding to the structure of entanglement. When energy flows through a region, it changes entanglement, and spacetime curves accordingly. The curvature we call gravity becomes a macroscopic reflection of quantum information. As this part of the chapter reaches its close, the direction of the story becomes clear. Entanglement explains why spacetime is connected. It explains why Einstein's equations resemble thermodynamic relations. It explains why minimal surfaces capture entropy, and it hints that space-time itself may be a vast network of quantum correlations. The next part will explore how these entanglement-based ideas extend beyond the ideal setting of anti-de Sitter space. The challenge becomes understanding how holography might apply to a universe like our own, one with positive curvature, cosmic expansion, and horizons set not by geometry alone, but by the evolution of the cosmos itself. Entanglement had already revealed its power within ADS-CFT, showing how geometry could arise from patterns of quantum information. But the more physicists studied this connection, the more they noticed that entanglement does not merely support geometry. It shapes it with extraordinary precision. The structure of space-time, its smoothness, its curvature, and even the existence of horizons emerge from the way quantum states are woven together. This discovery transformed entanglement from a mathematical curiosity into the central architect of space-time. Consider the behavior of entanglement in a large quantum system. When two regions share many entangled degrees of freedom, their states become deeply interconnected. Disturbances in one region influence the other in ways that cannot be explained classically. These quantum links do not require particles to move or signals to travel. They arise from the structure of the state itself. When viewed through ADS-CFT, these links manifest as geometric connections in the bulk. A region with strong entanglement corresponds to a region of the bulk where the geometry is smooth and tightly connected. A region where entanglement weakens corresponds to a stretched or thinned region of the bulk. This connection is so consistent that entanglement can be used to diagnose the shape of the bulk spacetime. By studying how entanglement entropy changes across different regions of the boundary, physicists can reconstruct features of the bulk geometry. Minimal surfaces that compute entanglement reflect the curvature of the bulk. When entanglement spreads, these surfaces shift. When entanglement contracts, they shrink. In this sense, the entanglement structure is the blueprint, and the bulk geometry is the construction. The thermodynamic interpretation of gravity deepens this connection. Jacobson's derivation of Einstein's equations showed that the curvature of spacetime arises from the way entanglement entropy changes when energy flows through small regions. Imagine a small patch of a horizon. When a bit of energy crosses that patch, the entanglement structure changes. This change corresponds to a shift in the geometry. If one assumes that entanglement entropy is proportional to area and that the flow of energy obeys the first law of thermodynamics, then Einstein's equations follow. This result suggests that gravity is not a force, but a response. It is the elastic reaction of spacetime to the flow of quantum information. Further research strengthened this picture. The work of Faulkner, Lukovich, and Maldacena extended Jacobson's approach to include quantum corrections. They showed that the semi-classical Einstein equations emerge from the variation of entanglement entropy in holographic systems. When quantum fields contribute to the entanglement structure, they produce corresponding corrections to the bulk geometry. These corrections match the expected semi-classical behavior of gravity. This result reveals that spacetime is not only built from entanglement, but continually updated by it. The geometry adjusts itself to maintain consistency with the underlying quantum state. Entanglement also plays a role in explaining why spacetime feels local. In the classical view, locality means that events influence only their immediate surroundings. But quantum mechanics allows correlations between distant regions through entanglement. How then does locality emerge? The answer lies in the structure of entanglement itself. When quantum states are arranged in a particular pattern, information spreads in a controlled way. The boundary theory encodes local bulk physics by distributing information across the degrees of freedom in a redundant manner. This redundancy resembles the structure of a quantum error correcting code, which protects information by encoding it across many qubits. In holographic systems, This redundancy ensures that local bulk observables can be reconstructed from different regions of the boundary. The bulk appears local because the information describing it is arranged in a stable, error-corrected pattern. If part of the boundary is modified or lost, the bulk can still be reconstructed from the remaining regions. This feature explains why spacetime remains stable even when the boundary system experiences disturbances. It also explains why gravitational interactions appear local, even though the underlying quantum description is highly non-local. The role of entanglement becomes even more striking when examining the interior of black holes. In ADS-CFT, the interior is encoded in subtle patterns of entanglement across the boundary theory. The growth of the interior, which classical general relativity describes as the expansion of spacetime behind the horizon, corresponds to the growth of complexity and entanglement in the boundary theory. As time passes, the boundary state evolves, and its quantum circuits grow more complex. This growth mirrors the classical expansion of the black hole interior. The connection suggests that spatial volume in the bulk may be linked to the quantum complexity of the boundary state, an idea that continues to be explored in modern research. Entanglement also helps explain the relationship between wormholes and information. The idea known as ER equals EPR suggests that entangled systems correspond to geometric bridges in the bulk. While these bridges cannot be used for faster-than-light communication, they reflect the correlations encoded in the boundary theory. Highly entangled states correspond to smooth wormhole geometries. Less entangled states correspond to narrower bridges. When entanglement disappears, the bridge vanishes. This idea supports the view that space-time connectivity is not fundamental, but emerges from quantum links. Each of these developments reinforces the same message. Entanglement is not a secondary detail of quantum mechanics. It is the foundation on which space-time is built. Without entanglement, space-time loses its shape, its curvature, its connectivity, and even its ability to support gravitational interactions. With entanglement, space-time forms naturally as a geometric expression of quantum information. As this part draws to its close, the next step becomes clear. Entanglement explains how space-time emerges in the idealized setting of anti-de Sitter space. But our universe is not anti-de Sitter. It expands. It contains a small positive cosmological constant. It evolves in complex ways that differ from the stable geometry of ADS. The next part of this chapter will explore how entanglement-based ideas extend into more general settings, setting the stage for the challenges described in the following chapters. Entanglement had revealed itself as the key ingredient behind the emergence of space-time in anti-de Sitter space. It explained how geometry could arise from a network of quantum correlations, how horizons acquired entropy, how the interior of a black hole could be understood in terms of boundary complexity, and how the smoothness of bulk spacetime emerged from patterns of information. Yet the question remained whether these insights were unique to anti-de Sitter space, or whether they represented something deeper, something universal. The universe we observe does not resemble anti-de Sitter space. It expands. It contains a small positive cosmological constant. It features horizons determined not by stable geometry, but by the evolution of the cosmos itself. If entanglement is the architect of spacetime, then its influence must extend beyond the ideal setting where ADS-CFT operates. It must reach into the structure of the universe we inhabit. The first indication that these ideas were not limited to anti-de Sitter space came from studying entanglement in simple quantum systems. When entanglement is arranged in certain patterns, these systems naturally mimic geometric structures even without referencing anti-de Sitter space. Tensor networks provide a vivid example. The mirror network, with its layered structure of entanglement, produces an emergent geometry that resembles anti-de Sitter space because the pattern of correlations flows outward in repeated scales. But other tensor networks, with different arrangements of entanglement, can mimic geometries that do not resemble anti-de Sitter space at all. This flexibility suggested that geometry itself emerges from entanglement patterns, regardless of whether those patterns take the exact form found in ADS. The idea that spacetime emerges from entanglement took a further step when researchers explored quantum error correction as a model for bulk reconstruction. The connection between holography and error correction did not depend on the specific geometry of anti-de Sitter space. Instead, it depended on the structure of entanglement in the boundary theory. If entanglement is arranged in a redundant pattern, bulk operators can be reconstructed from multiple boundary regions. This property ensures that local bulk information is robust against disturbances. The stability of spacetime, therefore, arises not from the geometry itself, but from the organization of quantum information. This insight suggested that the emergence of spacetime may be a general phenomenon, not restricted to a specific type of universe. Another clue came from studies of entanglement entropy in quantum field theories that do not live on anti-de Sitter boundaries. Even in flat spacetime, the entanglement entropy of quantum fields obeys an area law at leading order. This means that the dominant contribution to entanglement between two regions depends on the surface dividing them, not the volume behind it. This behavior mirrors the area scaling discovered in black hole thermodynamics. The recurrence of area laws in contexts far removed from anti-de Sitter space demonstrates that nature tends to encode information in ways that reflect boundaries, not volumes. This consistency hints that the holographic principle may be universal, even if its most precise form has only been demonstrated in ADS CFT. These patterns became even more compelling when examining cosmological horizons. In an expanding universe, regions of space become separated by horizons beyond which signals cannot reach. These horizons possess entropy. The entropy scales with the area of the horizon. It does not scale with the volume of the region behind it. This behavior mirrors the thermodynamic properties of black holes. Although the details differ, the underlying structure remains the same. The information content of a cosmological horizon is proportional to its surface area. Once again, nature reveals its preference for boundary-based information. Yet despite these promising signs, extending holography beyond anti-de Sitter space remains one of the greatest challenges in theoretical physics. Anti-de Sitter space provides a stable environment with a well-defined boundary at infinity. Our universe does not. It expands in time, and its horizons shift. A direct analog of ADS CFT does not yet exist for a universe with a positive cosmological constant. Attempts to construct such a duality include the de Sitter conformal field theory conjecture, which proposes a relationship between quantum fields on the boundary of a de Sitter universe and a dual gravitational theory within it. But this conjecture lacks the mathematical precision and robustness of ADS CFT. The boundary of de Sitter space is not spatial, but temporal, which complicates the interpretation of dual fields. Despite these difficulties, the idea that entanglement shapes spacetime remains compelling. Even if the exact holographic duality for our universe has not been found, many features of cosmology reflect holographic behavior. The entropy of horizons, the behavior of quantum fields during cosmic expansion, and the emergence of large-scale structure from quantum fluctuations all suggest that entanglement plays a role in shaping the universe. The challenge is to find the precise mathematical framework that captures these connections. Another challenge comes from understanding how to describe time-dependent geometries holographically. Anti-de Sitter space is static, which makes the duality easier to define. But an expanding universe evolves continuously. Its horizons shift, and its geometry changes over time. Extending holography into this dynamic setting requires new tools that can track how entanglement evolves in time. Recent work explores the idea that cosmic inflation, the rapid expansion of the early universe, may produce entanglement patterns that determine the large-scale geometry. But these ideas, while promising, remain under development. Even without a complete holographic description of cosmology, the entanglement-based view of spacetime continues to guide research. It provides a unifying principle that links gravity, quantum mechanics, thermodynamics, and information theory. It explains why area laws appear across such diverse contexts. It shows how geometry emerges from information, and it suggests that the structure of the universe may be encoded in patterns of entanglement that extend across cosmic horizons. As this chapter draws to its quiet conclusion, the direction of the narrative becomes clear. Entanglement serves as the architect of spacetime, not only in anti-de Sitter space, but in more general settings. Its influence reaches into black holes, quantum fields, and possibly the entire cosmos. The next chapter will take this exploration into new territory. It will examine the search for holography beyond anti-de Sitter space, focusing on attempts to understand how these ideas might apply to a universe like our own, one shaped by expansion and governed by a positive cosmological constant. The success of ADS-CFT demonstrated that gravity and spacetime could emerge from a lower dimensional quantum field theory. Yet this triumph came with a limitation impossible to ignore. Anti-de Sitter space, with its negative cosmological constant and stable boundary, does not describe the universe that expands around us. The cosmos we observe stretches outward with quiet acceleration, driven by a small positive cosmological constant. It contains horizons defined not by fixed geometry, but by the evolution of cosmic time. If holography reflects something fundamental about nature, it must extend beyond the special conditions of anti-de Sitter space. It must reach into the structure of the universe that gave birth to galaxies and scattered light across cosmic distances. The first place physicists turned was de Sitter space, the mathematical model of a universe dominated by positive vacuum energy. De Sitter space possesses a horizon much like a black hole horizon, equipped with entropy and temperature. The entropy scales with the area of the horizon, echoing the area law seen in black holes. This resemblance suggests that holographic behavior extends beyond anti-de Sitter geometry. Information in de Sitter space appears to be stored on surfaces rather than volumes. Yet constructing a holographic dual for de Sitter space remains difficult. The boundary of anti-de Sitter space is spatial and fixed, ideal for defining a dual conformal field theory. The boundary of de Sitter space, however, lies in the infinite future. It is a temporal boundary, not an arena upon which a stable field theory easily lives. The de Sitter conformal field theory conjecture suggests that such a duality might exist, but the idea remains incomplete and mathematically fragile. Cosmology adds further complexity. During cosmic inflation, the early universe expanded rapidly, stretching quantum fluctuations across enormous scales. These fluctuations were entangled, and their correlations became imprinted in the cosmic microwave background. The patterns observed in the sky reveal that quantum entanglement in the earliest moments shaped the largest structures in the universe. This connection hints that holographic principles may underlie cosmological evolution even without a complete dual theory. Entanglement across expanding horizons suggests that information does not simply fill regions, but flows across boundaries shaped by cosmic time. Celestial holography provides another direction for generalizing holographic ideas. Instead of working with a spatial boundary, celestial holography examines the behavior of particles and radiation at null infinity in nearly flat spacetime. The scattering of particles encodes information on a celestial sphere, where soft gravitons imprint patterns that reflect the symmetries of asymptotically flat gravity. These symmetries resemble those found in two-dimensional conformal field theories. While this correspondence is not as precise as ADS-CFT, it offers a promising hint that gravitational physics may always possess a holographic description, even when curvature is small or expansion dominates. Time dependence remains one of the most difficult obstacles. Anti-de Sitter space provides the luxury of a fixed boundary, but an expanding universe does not. Any holographic description of cosmology must track horizons that shift as the universe evolves. One approach introduces holographic screens, surfaces that encode information about regions behind them while adapting to cosmic changes. These screens obey area laws and capture aspects of holographic structure, but the mathematics behind them remains young. Without a stable boundary, defining a precise dual theory remains an open challenge. Despite these difficulties, patterns repeatedly suggest that holography is not confined to anti-de Sitter geometry. The area law persists across black holes, de Sitter horizons, and entanglement entropy in quantum fields. The behavior of quantum fluctuations during cosmic inflation echoes holographic structure. The symmetries of scattering in flat spacetime hint at a lower dimensional encoding. These clues reveal that holography is a universal theme waiting for its fullest expression. The universe may be governed by information at its edges, even when those edges evolve with time. The absence of a complete holographic dual for the universe we inhabit does not diminish the principle itself. It reveals where the next breakthroughs must occur. The search for holography beyond anti-de Sitter space remains one of the greatest quests in theoretical physics. It guides researchers toward the idea that space-time may not be fundamental but emergent, shaped by entanglement and encoded holographically, even as the cosmos expands. This insight leads naturally toward the next question, one that reshapes the understanding of gravity at its deepest level. Gravity feels fundamental. It shapes the paths of planets, binds galaxies, and anchors every movement in daily life. Yet the journey through holography reveals that gravity may arise not as a basic force, but as a large-scale expression of microscopic quantum information. Much like temperature emerges from the motion of molecules, gravity may emerge from entanglement and energy flow among deeper degrees of freedom that remain hidden beneath classical geometry. Black hole thermodynamics offered the first hints of this possibility. The entropy of a black hole scales with the area of its horizon, not the volume within. Entropy counts microscopic states, yet general relativity contains no such states. The smooth geometry has no structure capable of producing entropy. This contradiction points toward microscopic degrees of freedom invisible to classical geometry. The presence of black hole temperature, entropy, and evaporation suggests that gravity has a deep thermodynamic character. Space-time behaves like a system with hidden components, whose collective behavior gives rise to curvature and gravitational motion. Ted Jacobson's insight made this connection explicit. He showed that if one assumes that entropy is proportional to area and that the flow of energy through local horizons obeys the first law of thermodynamics, then Einstein's equations follow naturally. Geometry becomes not fundamental, but emergent. The curvature of spacetime reflects changes in entanglement and the distribution of energy. Gravity becomes the elastic response of an underlying information network. Holography reinforces this interpretation. In ADS-CFT, the geometry of the bulk depends entirely on the pattern of entanglement on the boundary. Strong entanglement corresponds to smooth geometry. Weak entanglement corresponds to stretched or disconnected regions. The Ryu-Takayanagi formula links entanglement entropy to minimal surfaces in the bulk, showing that geometry is encoded in information. This behavior mirrors the thermodynamic nature of horizons and supports the idea that gravity arises from entanglement itself. The emergent picture gains strength from the role of quantum error correction in holography. Bulk information remains reconstructible even when parts of the boundary are removed. This redundancy mirrors how emergent phenomena remain stable despite underlying complexity. Just as a fluid remains cohesive despite molecular motion, space-time remains smooth because entanglement distributes information across many degrees of freedom. The geometry appears stable because the underlying quantum code protects it, revealing space-time as a manifestation of informational robustness. Other approaches explore emergent gravity through statistical mechanics. Eric Verlinde proposed that gravitational attraction may arise as an entropic force, reflecting changes in microscopic degrees of freedom when matter moves. Although aspects of this idea face observational challenges, the conceptual insight remains influential. It echoes the broader theme that gravitational behavior reflects shifts in entropy and information rather than a fundamental interaction. The emergent perspective also offers new ways to interpret classical puzzles. Singularities, which appear as infinities in general relativity, reflect the breakdown of a geometric approximation rather than physical divergence. The microscopic structure remains finite even if the emergent description collapses. The information paradox becomes a question about how entanglement reorganizes during black hole evaporation, rather than a failure of physics. The early universe's entangled fluctuations reveal that cosmic structure has quantum origins, hinting that geometry itself arose from entanglement networks shaped during inflation. Yet emergent gravity remains incomplete. The microscopic degrees of freedom remain unknown. The connection between entanglement and geometry, while powerful, lacks a complete mechanism. Holography outside anti-de Sitter space remains elusive. These uncertainties mark the frontier, not a flaw. They reveal where physics must reach next. The emergent picture reshapes the understanding of gravity and prepares the narrative for the deeper challenges that define the edges of holography. At the boundaries of holography, physics enters a landscape where certainty fades and questions sharpen. These edges reveal not the weakness of holography, but its depth. They mark the regions where established principles collide, where mathematical precision meets conceptual mystery, and where the next breakthroughs in understanding must occur. One such boundary appears in the information paradox. Hawking radiation suggests that black holes radiate thermally, containing no information about the matter that formed them. Yet quantum mechanics requires that information be preserved. Holography offers a path forward by asserting that the boundary theory encodes all information about the bulk, ensuring unitary evolution. Still, translating this principle into a complete microscopic description of black hole evaporation remains a major challenge. The way entanglement evolves during the evaporation process remains subtle, leaving gaps in the current understanding. The firewall paradox deepens the tension. To preserve information, the entanglement between early and late Hawking radiation must restructure itself in a way that seems incompatible with a smooth horizon. Yet general relativity demands that an observer falling into a black hole experiences no violent boundary. Reconciling these conditions remains an active area of research, with no consensus reached. Some propose that quantum complexity or non-local correlations resolve the paradox. Others suggest that the horizon must undergo modifications, though such ideas challenge the equivalence principle. Wormholes present another frontier. In certain holographic contexts, entangled systems correspond to wormhole-like structures in the bulk. These structures reflect patterns of entanglement, not traversable pathways. Traversable wormholes require exotic quantum conditions rarely achievable. Whether wormholes provide a universal representation of entanglement or whether the connection applies only in special settings remains unknown. Time-dependent spacetimes pose a further challenge. Anti-de Sitter space allows a fixed boundary, making holography precise. But an expanding universe requires a holographic description that evolves with time. Holographic screens seek to address this, encoding information on surfaces that shift with cosmic expansion. Yet a complete mathematical framework remains unfinished, revealing a major gap in the ability to apply holography to realistic cosmology. The Planck scale remains another region of uncertainty. Quantum fluctuations become so intense that classical geometry breaks down. The number of degrees of freedom remains finite, yet their behavior is unknown. Approaches such as loop quantum gravity, string theory, and asymptotic safety each offer possibilities, but none has achieved experimental confirmation or full integration with holography. Cosmology also highlights the limits of current understanding. Inflation stretched quantum fluctuations across cosmic scales, leaving entangled imprints in the cosmic microwave background. Yet describing these processes in an emergent spacetime requires a holographic dual not yet constructed for a universe with positive curvature. Without such a duality, the connection between entanglement and cosmic structure remains only partly understood. These edges do not weaken holography. They illuminate its importance. They reveal that holography captures essential truths about gravity and information while pointing toward the deeper framework that lies ahead. At these boundaries, physics meets mystery, and the narrative turns toward reflection on what it means to inhabit a universe where space-time itself may emerge from quantum principles. To understand reality inside an emergent space-time is to accept that what appears fundamental may be the large-scale expression of quantum information. The ground beneath a person's feet feels solid, yet solidity arises from electromagnetic interactions between atoms. Space-time feels smooth, yet smoothness may arise from entanglement among microscopic degrees of freedom. Gravity feels fundamental, yet it may reflect the thermodynamic behavior of an underlying information network. Classical intuition evolved for survival, not for understanding the quantum foundation beneath geometry. Yet through mathematics and observation, humanity has gained a view far deeper than perception alone could offer. Black hole thermodynamics reveals that horizons possess entropy proportional to area. Holography shows that volumes may be encoded on boundaries. ADS-CFT demonstrates that an entire gravitational universe can emerge from a quantum theory with no gravity. These insights reshape the understanding of nature without discarding the truths of classical physics. General relativity remains precise and powerful. It predicts gravitational waves, black hole orbits, and cosmic expansion with extraordinary accuracy. Yet its elegance does not mean it is fundamental. Emergent phenomena often obey simple and beautiful laws. Fluids flow with grace despite arising from chaotic molecular motion. Elastic materials bend smoothly despite being composed of discrete atoms. Gravity may occupy this same category, expressing the collective behavior of microscopic informational degrees of freedom. The emergent view offers new perspectives on long-standing puzzles. Singularities signal the breakdown of geometric approximation rather than physical infinities. The information paradox reflects incomplete understanding of how entanglement evolves during evaporation. Cosmic structure emerges from entangled fluctuations magnified during inflation. Time itself may arise from the growth of entropy or the evolution of quantum information. The future of physics lies in exploring these ideas through theory and observation. Precision studies of black holes, gravitational waves, and cosmology offer clues about the structure beneath spacetime. Advances in quantum information reveal how complex systems encode geometry-like behavior. New mathematical frameworks may extend holography beyond anti-de Sitter space, providing a dual description for expanding universes. The emergent picture does not diminish the grandeur of the universe. Instead, it reveals its depth. It shows that reality arises from layers of description interconnected across scales. It shows that human understanding, though limited, can reach into the foundations of nature. It shows that the universe, no matter how intricate, remains accessible to the tools of science. The story of holography and emergent spacetime is not an ending, but a beginning. It opens a path toward understanding the universe not as a fixed stage, but as a dynamic structure woven from information. The cosmos may be emergent, but the quest to comprehend it is real, driven by curiosity, shaped by evidence, and guided by the evolving interplay of geometry, quantum mechanics, and the profound structure of entanglement.